Everything else set in this room?
Yeah, everything is fine. Thank you, Steven.
Yep, you have all your presentations uploaded?
Yeah, we managed to do that. It's all fine. So getting used to BBB anyway. So
Yeah, it's a great platform. I actually really like it. Did you remember to mark them all for be downloaded? Like, so have you seen the default slides, that little download icon in the bottom left corner of the slide?
yeah, I marked them all. Yeah, good point. Yeah, James told me yesterday. I did it. So
Okay,
cool.
great. Okay, so I'm just bouncing around. So good luck.
Thank you very much.
Bye.
Hi everyone. Waiting for my MC to start. I mean, I notice, given that Willie is online and is the first going, I don't know if you want to check the lights we've got, just to make sure. If you want to flicker through them quickly, I can give you the presenter role.
Yeah, sure. Let's give it a go. Oh yeah, these are the ones I uploaded, right?
Yeah.
Yeah, cool. I didn't change them, so that should be fine. What do I have to do? Can you see the red pointer that I'm moving
Yeah.
on? Okay, perfect. And if I would, I just click next, go to the next slide. Great picture. All right, cool. Seems to work. How do I give it back to you? Or shall I keep it?
You can keep it where I ran the introduction. And hi,
Alright.
by the way.
Can you claim it back if you need to? I don't have to do anything to give it you back, right?
No, I'll do that. It's
Perfect.
easy peasy. Thanks.
I'll mute myself. Actually, I should check my camera as well, I suppose, so you can see my mug. Is that working?
Yeah.
Perfect. It's stupid, right? I've got a laptop and both the webcam and the microphone are broken on it. So I have to have external everything, and then of course you have to change the defaults every single time you do anything.
No, it works.
Good.
A charm, yeah. I think I give it a couple of minutes more. We start.
Yeah,
3
yeah, it's the first
sharp.
one of the day, right? So,
Yeah. Right. So people are starting to join. I think it's 3 p.m. sharp here in the UK, so I think it's a time to start. First and foremost, I would like to say thank you very much for joining the Vfio Iommu PCI and micro conference today. We give a very short introduction first, and then hand over to the speakers, because I mean we have a packed schedule, very interesting topics this year, so it's better to start as promptly as possible. First off, I would like to thanks our sponsors, diamond sponsor Facebook, platinum sponsor IBM, gold sponsor are Microsoft, silver sponsors AWS, Netflix, and Red Hat. Speaker gift sponsor Collabora. T-shirt sponsor VMware. And conference services, Linux Foundation, and the service they provide to run the conference. Thank you very much to them all. Of course, we are running a conference in a friendly manner, and I wish we can run it smoothly. Well, here is the policy that should be well taken into account to participate in this conference. I'm pretty sure I will make sure that we adhere to it, and we work towards that. Well, respecting the code of conduct that the Linux Foundation put forward. So, housekeeping, whenever you not presenting, I mean, keep your microphone and camera muted, and when non participating. If you want to ask questions, I mean, it's up to every speaker to decide how questions can be asked. They can be asked through shared notes in the presentation here on VBB, or by enabling your webcam, and then, well, a presenter can hand over to you and ask you to unmute to ask that question. I will leave it to presenters to make that decision. I mean, whenever you start a presentation, just please explain how you prefer to take questions, if you want to take questions. Otherwise, you can take them at the end. And I would also like to thank the LPC 2021 Planning Committee. I think they did an amazing job again this year. I mean, for organizing everything and setting up this virtual platform. Hopefully it's going to be the last virtual conference, and next year we'll be able to run this in person. But anyway, I think it's a very nice platform that allows us to run this micro conference all together. And well, want to thank them all for organizing it again this year. Looking forward to next year as well. We are not on a break. Just to start with, before starting the micro conference, well, I would like to thank Alex, Bjorn, and Jörg for co-organizing it, and in particular Christoph, because well, thank you for showing up, and thank you for organizing everything. I mean, he may have become a familiar name with you, I mean, between conference speakers, and because I think he did an amazing job. I mean, this micro conference wouldn't be possible without your help, and I want to thank you very much today for the organization. Thank you very much for what you did to make this happen. Before handing over to Will for the first presentation today, I want to mention that it's a mixture of Vfio, Iommu, and PCI topics. That's for time and logistic requirements. So I think you can see that we'll go back and forth between, for instance, PCI and Iommu topics, but that's what we can do in terms of logistic. The schedule is quite packed, so please be aware of your allocated time slot. Well, you're all experienced speakers, so I mean, I'll have to stop you if you overrun. The idea is, as usual in Plumbers, we are presenting very technical topics, short introduction, followed by a discussion. Most likely we'll not be able to solve the problem within the time slot we are allocated. If you cannot solve it there, I mean, follow-up is in hack rooms. The most important bit is getting the point across. So let's not delve too much into the introduction. Let's get to the discussion as quickly as we can. We have, of course, a published schedule. I will stick to it, and I really mean it, because it's important for everyone to take part into the micro conference, first of all, for synchronization, and also for the breaks. It's very important to have breaks. So, I mean, I will stick to those breaks as they're planned. And in order to do that, and without any further ado, I will hand over to Will for the first presentation today, and let's get it started. And thank you very much, everyone, for joining.
All right, thank you very much, Lorenzo. And can you all hear me?
Yeah, I'll give you the presenter role, and I think you should be all set now.
All right, cool.
Feel free to go.
I'm just waiting for it to show up. Yeah, I still don't have it, Lorenzo. Well, while I wait to get presenter mode, oh, there we are, it showed up, perfect. Yeah, thanks for having me in the micro conference, because this talk is about these things called page-based hardware attributes, which some of you might be aware of, some of you probably aren't, so I'm going to describe it assuming no prior knowledge. But it's not really Vfio, Iommu, or Pci specific. It kind of touches on all of them, but it's, yeah, thank you for giving me a home for this talk, because it didn't fit anywhere else in the schedule. So let's get cracking. So I want to give an introduction. Like, normally I wouldn't do this at Plumbers, but I think it helps to give some background as to why me and why I'm interested in this topic, and why I need some help, because I don't know how to solve this problem. So I'm an active upstream kernel developer. I'm Will. And one of the main things I do, the biggest thing, is co-maintain the ARM64 architecture with Catalin, who I think is on the call as well. I work at Google in the Android systems team, so we're responsible for over 3 billion devices, and we're responsible from them in the sense that we maintain and develop this Android common kernel, which is essentially a kernel tree which you can use to build Android products with. And we are SoC agnostic in this team. We don't just work on a specific SoC or for a specific OEM. We work with everyone trying to make an Android device. And therefore, we get some visibility into upcoming SoC designs. And because we're upstream first, we can sometimes get an idea of, oh, SoCs are going in this direction, and Linux kind of doesn't have any support for that. What might it look like? And these page-based hardware attributes are really, they fall into that category. We do have some active engagements with the ARM architecture, but as you'll see, that hasn't helped that much for this specific problem. So I said I'd assume no prior knowledge. So I'm going to give a quick recap. Lots of details omitted, but to set the scene. So this is kind of what the ARM64 MMU looks like, and the CPU and the SMMU, which is what they call their IMMU, are basically the same. Like they've had the same table format and things like that, same kind of procedure. So these green boxes represent different exception levels. So EL0 is user space, EL1 is kernel, EL2 is hypervisor, it's more privileged. And in this sort of light blue box I've got here, you've got user space and kernel, and when they emit memory accesses, when they load and store data, they'll do that using virtual addresses, right? So those virtual addresses, these VAs, come out into the stage 1 MMU, which reads the stage 1 page tables, which are owned by the kernel, and they're used to translate that virtual address into an intermediate physical address, which is this IPA, which comes out the other end. And then this IPA is used as input to a stage 2 MMU, conceptually. And that reads a stage 2 page table that's owned by the hypervisor. And then that translates the intermediate physical address into a physical address. And the physical address that you get out at the end of that is actually what's used to go and index caches. It's used as put on the bus as a transaction to go and actually get some memory. So the page tables here are used for address translation, but also normal permission checking, read only, execute never, things like that, and memory attributes. And that's quite crucial to this talk. So memory attributes might be things like, is this a cacheable access? It might be things like, is this a shareable access? Does it need to be coherent with other CPUs? Those sorts of things are encoded in the memory attributes, which come in by the page tables. And I should say, in terms of asking questions, please do just shout. It's easier if you put your video on, but don't let that stop you. People need to understand the problem, otherwise it's going to be silence at the end. So please do shout if I don't make any sense. So then this sort of abstracted view, rough overview of the ARM64 page table format. Again, this box down the bottom is now this SMMU, or sorry, this MMU could be the SMMU. So that's doing your stage 1 and stage 2. The virtual address goes in. It either faults or emits a bus transaction. And when it goes and reads the page table, it roughly gets this sort of information out of the page table. So whether it's valid, the output address, which for the full translation is going to be the physical address, some permissions that I mentioned earlier, the attributes that I mentioned earlier on, and this mysterious thing at the top called PBHA, page-based hardware attributes. Now, these are 4 bits, I think I remember that correctly, in the page table, and they are not used or interpreted by the MMU in any way. These 4 bits are basically just taken from the page table and emitted directly out as part of the bus transaction. So assuming you don't fault, you get your physical address, your attributes that I mentioned, and then these mysterious 4 bits just get put on the end of the transaction. So what are they for if the MMU is not actually interpreting them? Well, we can look at the ARM, and if you've ever read the ARM, it's all kind of written like this. So it says when PBHA is enabled, then hardware can use that PBHA bit, because you can actually enable it on a per bit basis, but assume they're all enabled. So you can use those bits for capital letters, implementation defined purposes. And then there's some spiel about how if they're 0, it's kind of the same as if they're disabled. But what this means is those bits that end up going out on the bus, those weird 4 bits, do some weird implementation defined thing that even ARM haven't specified what it does. It's up to the SoC integrator what impact that has on your system. So unsurprisingly, we disable this upstream, right? Because we have no idea what these bits do. So yeah, implementation defined means we have no idea what they do. I mean, you know, halt and catch fire could be one of the encodings. I've got a bunch of questions here because trying to find out what people are building, what people think is reasonable to support, what isn't reasonable to support, what could they be used for. I'm going to come back to this at the end. I've only got a couple more slides. So I would like to give an example of how they might be used in the modern SoC to kind of do something useful. So an example of how they might be used, here is a, that's not even an SoC diagram, right? It's just a block diagram showing part of an SoC or an overall image. So on the left-hand side, I've got these standard ARM IP blocks, so CPUs and some caches up here. So it's interesting, actually, the PBHA bits don't form part of the physical tag in the caches. So if you have 2 accesses which have translated and got to aliases of a page or a cache line, and they have different PBHA bits, they'll still hit in the cache. The PBHA bit is not taken into account for the tags. On the Iommu side, over on the other side of the diagram, the SMMU actually overrides the PBHA bits. So the DMA master might decide to stick some out, but they're going to get overridden by the SMMU. It can put whatever it likes in there, and that's, again, programmed from the page tables. So the transaction comes out, goes onto the interconnect, that propagates those bits. And in this example here, there's this thing called a system level cache in SLC. This is quite popular in more modern ARM64 SoCs. And this is essentially an invisible cache, is one way of explaining it. It's a cache that lives right before DRAM, so it kind of looks like it's next to the memory controller from a software perspective. No one accesses memory downstream of that. So therefore, it's able to cache all transactions. It can buffer everything before the memory controller. And you might be able to use these PBHA bits to influence how that SLC behaves. So for example, you might be able to put performance hints in there. You might be able to put prefetch hints in there and control how a prefetcher is going to start prefetching data into the SLC based on some access patterns. You might be able to influence caching policy beyond the allocation hints that the architecture provides. So for things like eviction policy, you might be able to control with these PBHA bits. Quality of service, so whether something it's high priority or low priority, or whether something should be, only access certain sets in the cache, for example, the geometry of the cache. And perhaps most scary of all, you might use them to actually influence the format in which the data is stored in the cache. That's quite scary, because if you have different aliases accessing the same page with different PBHA bits, you can have loss of coherence if the data format is different depending on which one hits, or they're not part of the tag. So you could run into some quite worrying problems with that last data format one. So if we were to take that SLC example that I just gave, what would it take to support it in Linux, and what are the sort of problems we run into? So one is that the ARM architecture it's very vague, as I showed you, about what these things do. It doesn't even specify how the stage 1 and the stage 2 interact. If you remember, there's 2 page tables, one owned by the kernel and one owned by the hypervisor. They both have PBHA bits. The architecture doesn't define how they get combined. You have to go and see what your specific CPU does. I think most of them take the ones from the hypervisor in preference to the ones from the kernel, so stage 2 overrides. But again, that's really difficult for Linux, because it means we have to enable this on a CPU basis. although it's 4 bits in the page table, you don't know how many bits are actually supported by the CPU, and there's no way of probing that. So we need to know that somehow as well. And no ID register tells you that. As I said, the data format changes appear to be infeasible. You'd need to make sure that all virtual aliases somehow efficiently do this are congruent. They all agree on the PBHA bits. And that's not just within the kernel, that's user space, that's kernel, that's hypervisor, potentially firmware and secure side as well. And if you have a presence of a cacheable alias with incorrect bits, like the linear mapping, perhaps something could go wrong there with speculative fills, I don't know. But the performance hits, I think, look a lot more tractable. We would need a firmware description to say how these bits are encoded. We would require them, I think, to be static. You wouldn't want, encoding OXF to mean one thing when you boot the system and then a day later to mean something else based on, I don't know, firmware changing its mind. You'd want them to be statically assigned. If you wanted to use them for drivers, which is quite a common use I've seen, where you want, essentially, you're interacting with a certain device, you want to program up the SMU in a certain way and the CPU in another way with these different PBHA bits. You could possibly do it with DMA ATRA, but it does end up looking very opaque because we don't know sort of how do you name those things. You end up with things like DMA ATRA PBHA 0000, DMA ATRA PBHA 0001 as these hash defines. It's not great to read. It's also per page mapping, right? So they call them page-based hardware attributes, but it's not per physical page, it's per the mapping. And it's also not per transaction. So things like performance hits are a little weird because you're saying this buffer that I'm mapping it so that this part of it needs to be streaming, or this part of it needs to be higher priority than this other part. But it's not done on a per transaction basis. So you would probably want a mechanism to be able to remap your DMA buffer, the same memory, but with different PBHA bits. And it's not clear whether we need this only for these sort of driver cases, or whether we also need it for anonymous memory, for example, whether you want to allow anonymous mmap or mprotect to be able to change these bits for user space mappings. For QoS, in terms of partitioning, maybe do it with res control, but again, it's all opaque, so I don't know. And I'd be keen to hear of any practical use cases that I've missed that people know about or are interested in. And I think that's all I have. So how do we fix this? I'm not quite sure how to support it, but I do know that SOCs are building this. It is being used for some of the sort of things I've outlined here. I'm not sure how to really go about getting Linux ready for this. And I'll go back to some of the questions I had before just to try and prompt some discussion, but I'm keen to hear from other people who either know about this or have thought about it, or where do we draw the line? So thank you. That's kind of the outline of the problem.
I've been in a number of conversations on the Intel side for the TPH bits in PCIe, which are very similar. They're very implementation defined, and every SoC, has a particular take on how they work and what they should do. And we've wanted to see it exposed in Linux. One of the SoCs I'm familiar with is using those bits to target the basically kind of, you said cache sets, so very similar to that. So where the physical cache exists on the SoC, and there's reasons why certain memory DMA flow should go to certain cache areas or not. Yeah. But we want to have a generic. Jason,
is that done on a per transaction basis?
So TPH bits in PCIe are per transaction basis.
Okay, yeah, so that's a crucial difference to how, the way it's designed here, right?
Yeah, and I think it's an ARM philosophy versus an Intel philosophy, because Intel often tends to put things on per transaction basis, and ARM often puts things into the page tables. And I'd be interested if there's some sense of harmony here, like what happens to TPH bits in an ARM SoC, like the one that I know of. They're being used like your PBHA bits are being used, where they come into the internal interconnect. And we probably don't have PBHA on this hardware at all. So I view them as very, very similar. Other than
that's interesting, actually, what you said, because the SMMU has no provision for passing the bits through. So it always overrides them with the page table.
I was just looking at no snoop, and I wonder if it would be similar. Like the no snoop bit coming in from a TLP on PCI overrides the cacheability bits in the memapter on ARM. And I wonder if ARM would do a similar thing with PBHA and the THP bits.
Yeah, let me make a note to follow that up. THP.
TPH, sorry.
TPH. Bits.
But at least from a kernel perspective, I think if a device driver wants to use SoC-specific transaction hints, either encoded in the page table or carried from the DMA originating at the device. That's where we need, I think, an infrastructure.
Yeah, I agree. So what else have we got? Peter says, do you have an example of an SoC that implements these things, and do we know what they actually do there? So the example I gave for the, I mean, I know it was a bit high level. So this one with the system level cache. So using this for controlling the caching policy. So it's in a way which doesn't break coherency. I've seen that sort of thing being done. So you can influence, you know, the behavior of the SLC, but not in a way that's visible outside of just performance changes.
I will.
Hey, Kathleen.
Yeah, that's what I've seen internally as well, on using the PBHA to drive some cache allocation in the system level cache. So still be fully coherent, so we don't have a problem with that. It's just that some of the accesses would avoid polluting the system level cache.
Mm-hmm.
And from this perspective, it's not too bad. In terms of the DMA API, I thought we'd add some maybe device tree only without some DMA attribute, custom attribute 1, custom attribute 2, whatever, and you have a corresponding bit value in DT, and we just map to those. But that assumes that it doesn't break coherency.
Yeah, absolutely. So I think that's probably one of the it's a line that I think we need to draw, which is in the face of mismatched aliases, so 2 virtual aliases which differ on PBHA bits, do we require coherency? And I think if we say yes, then it makes this problem much more tractable. If we say no, then I don't know necessarily how to address that.
I mean, it's better to, you probably heard from more people than me on what they use this for, so get in touch with them and ask them. And just, we propose some patch set on the list and get them to comment. If they keep quiet, then yeah, we won't support the feature at all.
No, I agree. And I mean, part of me speaking here today is because I have been obviously talking to silicon vendors, and I'm aware of some of these things that are going on because just say implementation defined is kind of a bit of a free for all. So it's how do we rein that in a way that we can support it in Linux? Because getting rid of all the aliases I mean, it's even just within the kernel, it's a pretty expensive thing to do. It looks like the swap out path pretty much.
The DMA API would have to unmap the pages from the linear map.
Yeah, you end up going through the RMAP code or something like that to go and find all the mappings of that page.
Well, not necessarily. Well, yeah, maybe. Yeah.
It depends. I think it depends on the other question. It depends on speculative. Like, is there speculative access allowed to cause a problem? And probably, if it's caches, it probably can.
No, it depends. If it's a driver, and let's say a graphics driver that allocates some memory, and it wants to access in multiple the system level cache, that's one thing. So the driver is in control of what
That's true.
What it allocates. But if you have some random, as you mentioned, you have them anonymous maps that one wants to or change some of the or whatever you want to do, change the format in the cache. And then that gets a bit more complicated to sort out and avoid the aliases.
Yeah, I think you end up with something like it's awful. You have to extend get user page basically to like the GUP code. You have to take the PBHA bits that it needs, and then it has to find all the aliases. It just sounds, a million years later when it comes back.
Does the secret MFD thing help with the infrastructure that it has to unmap it from the linear map?
I don't know. It's not just the linear map though, it's also user space, right? So
yeah.
At least for an API, the use cases I've seen, at least in the server area, tend to revolve around NUMA effects. Like, I'd like to allocate some memory on my local NUMA node, and I would like to tell the device to DMA into that memory, and I would like it if the device, the whole SoC under me targets the DMAs to land in my local NUMA cache. I don't know if that's what you're seeing in other vendors, but that's definitely kind of my thinking what this is being used for, what I see.
Yeah, that's one I hadn't got. So I mean, obviously I'm from the Android background, so we don't have the big Numa things. But that's I could see PBHA is not limited to Android, so I could see it being used for that as well. So I'll mention that. Thank you. Right, what else do we have? We've got a few more minutes. Ner's mic is broken. So there's a conversation between Ner and Mark. Don't know, Mark, do you want to talk about that?
Well, it was just Ner did seem to think that firmware could somehow define what these bits were meant for. But my understanding is that this is baked in the hardware and not something that software can control in any way other than setting them or clearing them.
Yeah, I suppose. So firmware would have to advertise, or DT, as Kathleen said, would have to advertise to the kernel. You know, these are the bits encodings that you have. I guess assume that they're the same across big little because it doesn't bear thinking about otherwise. But then I don't know how a driver would pick that up.
Also associate a semantic to that.
That's exactly, yeah, right. So
Yeah,
maybe you would have to name them or something, which is pretty
Yeah,
horrible.
I mean,
and the
that's
driver would have to say find the one that means high priority, and it goes, oh, that's E, and then you go and use that.
Also, find the one that is safe, for example, for running a guest, for example, because the lack of definition of what these bits, I mean, how these bits are combined between stage 1 and stage 2. I mean, today, I strictly have no idea how a guest can potentially exploit that against the host. It's mind-boggling.
I think that means more generally that we cannot support any system where these bits potentially result in loss of coherency, even ignoring the idea of whether drivers can use them because of potentially malicious guest that exists.
Yeah, I mean, I think most CPUs do like stage 2 overrides. So if we could if that ended up being, we require that for Linux, then at least a malicious guest would be out of the picture, I think.
Sure.
But it sounds like there's not much of an appetite to support the loss of coherence case.
I don't think unless the memory allocated is controlled by the driver, but even that one is not.
No, that's fair actually. So you could have
some survey of what people use it for. We tried to push this internally through the architects to clarify the meaning here and what people are allowed to do and not to do. Didn't have much success. At least enforcing not breaking coherency here. But yeah.
But I think what you said was fair, having an allocator, like a DMA buff allocator or something, which could dish out, a bit like carve-out memory. You could have some memory which that you don't have an alias of, and that you're going to have these bits. So that might be doable for coherent DMA allocations.
Yeah, but
streaming DMA.
Will be limited to this kind of DMA, not changing attributes of user mappings.
Okay,
I
cool.
think you ran out of time.
I'm out of time, yeah. So Lorenzo, thank you very much. Thanks for everyone who joined in. It's given me some food for thought. If you want to follow up with me offline, I think it's will@kernel.org. I think I had it on the first slide.
I think Will wanted to mention something, that the challenge there is probably also to map those attributes to something that is common for the kernel, I suppose, is something that every platform should define. But having a base use model for the kernel to say these specific flags and then map those bits to those flags to make sure that we can use them, maybe it's something that a way forward. Well, I understand what you presented, but well, that's the challenge probably.
Yeah, I mean, we need a way that drivers can portably interact with these things across different SoCs and not have to say, am I on this SoC? Oh, I need to use this encoding. Oh, am I on this one? I need to use this encoding.
Yeah, I mean, just saying that what for Linux those classes mean, and then map those bits to those and see if we can use them or not. I mean, that's I suspect what will happen, but well.
Cool. Well, thank you very much. I don't want to eat into the next bit, so I will stop. And like I said, please follow up if there was something you want to tell me about use cases or something you missed, or you think of a question afterwards that you didn't have time to answer. So cheers.
Thank you very much, Will. Thank you very much, everyone who took part. I mean, we have a 5-minute break now, and we restarted well in 5 minutes. And thank you very much with Jonathan presentation. Jonathan, giving people some time to come back.
Figure out how to turn the camera on.
As you wish.
Sit here and wave until people turn up and see if it turns up on the other computer. Yep.
I think it's time to get started. Just I give you presenter role, and then you're all ready to go.
Okay.
You should all be working, so feel free to go anytime.
Thanks, Lorenzo. Okay, so this next talk is going to be on a stack of different elements, and to be honest, it's not a perfect plumbers talk, because what we actually have here is a series of different topics that are all closely related, each of which has a pile of questions. So we'll probably end up with a short intro, some time to talk about something, another short intro, some time to talk about something, and inevitably we'll run out. And in fact, I'll just stop my stopwatch. So why are we discussing these topics at all? So DOE, and I'll come on to the details of what that is in a minute, is necessary for CXL 2.0 enablement, particularly to access a sort of device provided table, looks a bit like an ACPI table called CDAT. CMA itself is likely to start appearing on devices fairly soon. On top of that, both PCIe and CXL IDE, which is a form of link encryption, is likely to also appear fairly soon. And one other thing here is it is actually quite useful to prove out what we've done in the DOE implementation using several different protocols. There were some open questions on when we first did CDAT that were best resolved by just doing a few more. As we went through this process, it turned out there were an awful lot of unknowns, and hence plumbers seemed the obvious choice. So as I mentioned, this set of slides are going to, this session in this microconference is going to be a little unusual in the sense that it's going to be looking at a stack of different elements. There are questions on all layers. I've gone with this green coloring to indicate slides on which I'm expecting questions. By all means, jump in with questions on other slides. As I put in the chat a moment ago, I've got a slightly precarious arrangement for reading the chat. So definite preference for audio if possible, or if anyone else can shout out if there's a particularly interesting question popped up in the chat. Yeah, not sure how far we'll get, but hopefully at least slide 8. There are quite a few slides, many of which I don't actually intend to get to. They're there for sort of background information if people want to look at them later. Going to start at the low level and then sort of build up the stack so that hopefully we can make some progress even if we don't get all components in place anytime soon. I'm going to try and avoid actually too much discussion of any code or indeed specifications, mostly because we've only got 45 minutes. There are interesting little nuggets in there, interesting corner cases that do need discussion, but that's probably better done on the mailing list. I will add that use cases for this are also very much of interest. Particularly, do we actually want to support all of this in the kernel? Is it worth bothering from a maintenance point of view, or is it actively a bad idea? I'd be interested to hear anyone's thoughts on that as we go. So, an introduction. It's a stack of different components. So at the bottom end, we've got PCI Express, and particularly this entity called a data object exchange capability, which hides in config space. And that provides a sort of mailbox-based transport for query response type protocols. One of those is CDAT, which I mentioned a minute ago, which is a table used particularly by CXL, although it is more general. Then on top of, another DOE protocol is CMA, which we will cover rather extensively later in this. And that's known as component measurement and authentication. And that provides a DOE transport for the security protocol and data model, SPDM, which we'll also touch on. The other one that I've put on here, but don't intend to spend a lot of time talking about unless anyone wants to jump in on it, is integrity and data encryption, IDE. This is link encryption, and also there's a thing called selective encryption that lets you do point-to-point through switches on PCI Express, particularly for things like peer-to-peer you can route the data between two devices and encrypt it on the link in between them. If anyone is interested in kernel managed IDE, please shout out, because it would be useful to identify who cares, so that we can have some more discussions about that at some later date. So topic number 1, the DOE. The PCI SIG ECN for this defines a mailbox interface in an extended capability in PCI config space. There's an in FIFO and an out FIFO, both 32 bits, so 1 DWORD each. And for the in one, you just write to it, DWORD after DWORD after DWORD, to get a whole message in. For the out one, it's a little more fiddly. It's a read from it and then write anything to it just to acknowledge that you read the previous value. There's an interrupt for things like, is the response ready, error conditions, and a slightly odd one, which is no longer busy, but we won't touch too much on that today, but the handling is a bit strange for that. It's kind of hard to have an interrupt for something is no longer the case, and you can't tell whether it ever was the case, but you have an interrupt. So it's a little bit strange. This ECN includes a protocol format for what's known as the discovery protocol, which is kind of crucial, because the only way of finding out what the DOE mailbox is for, and you can have multiple instances of these per PCI function, is to use the discovery protocol. Now, as we'll come on to, the problem with the discovery protocol is you can break anything else that's going on at the same time, because you can read someone else's data, for instance. Each DOE instance can support multiple protocols. There are restrictions in some of the other specifications that specify individual protocols. For instance, CMA and IDE can share a DOE instance, but you can't have anything else on that one. The protocols are effectively labeled by vendor ID and a data object type, which means that vendors get to define their own, which is always fun. And we'll get some questions on that a bit later. Okay, and as I say, yes, other published specifications define some protocols. So this is the set we have to look at today when considering how this stuff works. There are other protocols. Some of them are vendor specific, and some of them are in various organizations and not yet published, so we can't talk about them. So this is our first issue, and it comes in several different forms. There is no way in the way that the hardware works for DOE to do mediation. So if there's more than one piece of software wanting to talk to this DOE instance, they can trample on each other. There's no convenient, I've claimed the DOE flag or anything like that. They may be used by any of, and this is a partial list, the kernel, user space, a hypervisor, trusted execution environment, so something like TrustZone might use them, firmware in the system, others. You can have slightly interesting channels from secure elements and things that will talk over the PCI bus to these. And as I mentioned earlier, by the time we know what a DOE supports, it could already be too late. We could already have broken someone else using it. So we can't do any decisions for who has control of a DOE simply based on what it supports. And as I mentioned CDAT earlier, for instance, the expectation is that firmware might use that during a sort of cold boot situation, but the software model based on CXL at the moment for that will use it from the OS kernel. And as I say, if we want to know it's a DOE mailbox, we've just killed IDE, broken the encryption and made the device die. So it's not helpful.
This, Jonathan, is because, sorry, is because discovering the protocol use the same mechanism as the protocol themselves, right?
Absolutely, yes. Thanks, Lorenzo.
Thank you.
Yeah, clarification. So step one, which is kind of the easy one. So I thought we'd start with the what I think is the soft question. So we have had discussions about the fact that given these protocols can be defined by vendors, there is an argument for giving user space access to them. There might not be a kernel driver for some types of component, particularly CXL devices can, particularly CXL1, for instance, can be set up by firmware, and then the OS just doesn't do anything at all with them. They're just memory from the point of view of how they're used. But they could, in theory, have DOE instances. And there are other types of protocol where it definitely makes sense to expose them to user space. So we need to mediate between anything accessing them from user space and any kernel accesses, so that again we don't trample on top of each other and end up corrupting each other's data streams. And there's certainly no reliable way we can build the kernel such that it's hardened against bad implementations in user space if we expose it to both of them directly. So option one for this is that the kernel implements protocol support for any protocol we're going to deal with. Then on a per protocol basis, we might have a user space interface. CDAT's an example. For that, we just had a table dump type interface, similar to the ACPI sort of debugging and the ability just to dump a table as a binary, which is quite helpful for debugging. Option two would be that the kernel would provide some generic access for some protocols. So the RFC, or one version of the RFC, includes an IOCTL type interface where you can go, here's a query, put the response here, run that. Whether we want to do that, because we get into interesting questions of if we provide this access to user space and then we do something in the kernel later, there are cases in some of the protocols where there are sequences of query responses that have to occur in the same order, or you can successfully corrupt yourself. And another option is that we may have a sort of optionality to this. The kernel sometimes, in some sense, binds to a DOE and indicates that. If that happens and we're not, if that doesn't happen and hence we are not bound to it, do we need to prevent user space access, or do we need to allow user space access? Kind of an open question. And the sort of final open question on this one is that protocols can be defined by vendors. So the usual vendor defined element, how nice should we be as the kernel community in enabling vendor defined protocols without them putting them in the kernel? So on that note, do we have any sort of feedback? We have a question from Ashok. DOE does DOE have just one outstanding message at a time, or can it take multiple commands and responses? It's actually a slightly interesting question. Per protocol, it's only allowed to have one query response going at a time. But if you implement multiple protocol, the specification allows for you to have multiple query responses going on different protocols simultaneously. Now, so far in the kernel support, we've decided that there isn't really a strong use case for that. And it doesn't half make the implementation more complex. So it's a kind of, we'll solve it when it's necessary and not any earlier. So Jason's asked the good question, which is there any chance to go back and fix the spec and maybe add some form of hardware-based sort of mediation in this space? The answer to that is we can't fix the DOE spec as has been issued, which unfortunately means that people are making hardware. None of it's out there yet, but we unfortunately are a little bit late to do anything about it. We absolutely can have inputs to future versions of the specification. And should we say, having identified some of these issues, I have had some feedback from people involved with the spec process, which is they would like more involvement from the kernel community at an earlier stage to catch these things. Lessons learned, perhaps. So anyone got a view on any of these options? My current preference is one. Sorry, go ahead, Mark.
No, I was going to say, it sounds like for some of the things like you mentioned, like IDE, we are likely to want to use that in the kernel at some point or other because of things like protecting against external Thunderbolt stuff and whatever.
Yep. That's a good point. I've got some suggestions on that on the next. Oh, okay. Sorry. There's a very brief slide that just says is justifying the fact that we will want to use these things in the kernel. This is just a bunch of use cases, so I'll skip over that in the interests of time. So this is the next question, is if we've got other software entities, kernel user space is kind of easy because, to be honest, we effectively control it. The problem we get is when things like trusted execution environments are involved. Now, for this, they may be chatting away to the thing, and at the moment, we can't, as a kernel, people rely on the fact that they aren't, and that's a bit of a problem. It's quite a big problem. We can't get away with the kind of obvious solution, which would be to put a DSM in ACPI. So this is just a query to the firmware that basically says, give me some magic property, and it's GUID indexed. So we could, in theory, add one of those. The problem being that we also need to support hot plug, and DSDT, where the DSM would be, would not, but doesn't perceive, it doesn't understand the concept of devices that weren't there when it was created. It's not a dynamically updated table.
Well, if it's hot plug, is there any chance that it's actually being used by the firmware?
Yes, there are definitely models where that happens, and it gets a little bit exciting, to put it lightly. A lot of this, I will touch on the fact there is stuff that we cannot discuss at this point. So that sort of question should get clarified in specifications that will be forthcoming. So we may well want to talk about those next year, or possibly sometime in the meantime. I did raise the question at the bottom here. I've got some suggestions for how we might work around this, but I would add that in the meantime, we may need to just use something horrendous like an allow list or kernel parameters that say, for instance, this one here is CDAT. There's no way we can trample on firmware if we're reading CDAT. So we may need those sort of options to get us going. Yeah, agreed with Bog. So yes, his microphone's died. So a couple of quick suggestions. I don't want to go into this in depth because honestly, we'll rat hole badly on options of how to do things in ACPI. I noted earlier, actually, I only care about ACPI, but obviously there would be other firmware stories for this or other methods needed. We could get away with, in the short term, a system-wide DSM, which just basically says the firmware does perceive or does understand DOEs. It's going to provide a firmware-specific interface to talk to them, and all the mediation is actually going to be done in some firmware element. It's a big hammer, doesn't work in all cases. The hot plug case is interesting for that, given that the firmware possibly doesn't even know the hot plugs occurred, depending on exactly what model you use. There are other options. We could do something similar to is done for fit, which is a technique used for updating NFIT, which is an NVDIM related ACPI table. And what that does is it adds a method which you can query at runtime that gives you back a buffer. Inside that buffer, you then have some descriptive table elements that tell you current state. That can be magically routed through to memory somewhere that's been filled in by someone. And you can take ages to reply to that. So you can go out and ask some management controller and have it come back and fill the buffer in. It's not a trivial spec change, but we probably do need to try and get something in place in the space, and I propose we do something code first, so hopefully we can get good agreement amongst the kernel community and other operating systems on what this would look like before we get into the games of actually getting it in a published spec, which can take a lot longer. Anything else in the chat at the moment? Any other comments on this before we move on to?
So for the question between user space interfaces and kernel interfaces, if there are vendor-specific extensions, then I think we'll have to do a user space interface. And we have other subsystems like I2C or USB that do have methods of allowing and disallowing user space access to devices based on what other drivers are bound to the kernel, and I think we can just duplicate whatever is done there.
I wonder if we want to go that route or go for effectively option 2 here, where we provide a very tightly controlled interface so that you could talk, particularly if you've got an instance where it's supporting, say, CDAT, because you can combine anything with CDAT. There's no rules in that spec, and a vendor-defined protocol. So you'd need to do the mediation there just to make sure that you do your queuing and interrupt handling and everything. So we might be better off always binding to a DOE, but providing CharDev with IOCTL.
Yeah, didn't quite understand how it works if there's multiple protocols, like how the kernel would arbitrate between those. It sounded a bit like every single protocol could be modeled as a read-write type interface, not even IO control. So you can just read and write and pass down the data stream to user space that way per protocol. But if that's not possible, then
you could. There's a few things about indicating that you've finished. So you need to write a certain amount of the length of the record is protocol specific. So you almost need a how long is it field to be filled in,
okay.
which is a little bit fiddly.
Well, that's a length and read and write.
Yes, yeah, you could define you could define a format to do it via read and write. Absolutely, that's certainly true.
And if it's vendor specific, then the kernel wouldn't have any idea how many bytes it needs. It has to come from user space anyway.
Yes, yeah, absolutely.
Couldn't the vendor protocols be put on a different mailbox?
Ideally, yes. In practice, that doesn't say so.
Okay. Well,
I wish.
I guess my suggestion to vendors is put it on a different mailbox, because if because then it could be a different channel, so to speak.
You've still got some slight problems around the discovery protocol. So particularly if you've got a generic class device that's supporting a vendor protocol. So you've got something like a CXL Type 3 device, which is just a memory device, which is done as a class and has one unified driver. But you might have a vendor telemetry protocol or something, or I don't know, error reporting that you push out. Ideally, yeah, you'd have it on a different mailbox, but you'd still need to be able to say, you can't have it now because right now I'm doing the discovery protocol on it to find out whether it's my mailbox or yours. But yeah, it could be
true. But the kernel mediation for that is easier, right? Kernel can enumerate those and then hand it off to user space via some request. If the vendor really needs some user space direct access.
Yes.
Yeah, that seems. Yeah, I don't know. Okay, thanks.
Dan's just appearing. Hey, Dan. Any comments on this one, Dan, before I move on?
Did you already talk about the vendor specific part of it?
We did talk a little bit about that and sort of ended up with the conclusion we need to provide some provision for it. And the point was just raised that it would be extremely helpful if it was a different mailbox from
it would be helpful if it was a different mailbox that the kernel didn't own at all. Yeah, the only thing I wanted to raise there was the fact that like we have ACPI DSMs, and those are vendor specific. Any vendor can define them at any point in time, but we don't give user space a generic way to issue any of them. We wrap kernel interfaces around them. So I don't know if we want to let, or if it helps Linux to let vendors run wild with DOE interfaces versus like saying, no, you got to kind of follow protocols and publish them. And then of course, Linux will support the published ones. But yeah, if it's on its own DOE off in the corner, then maybe we can't enforce anything there.
I mean, that might be an interesting policy to say, that is, if your protocol is going to share a DOE with one that is defined in a specification, then you've got to do that process. If it's an entirely separate one, then we can do the stuff that Ira just mentioned, where we just hive it off and go, nah, it's not ours. You do what you like with it. So that might work very well.
Dan, you're saying that if it is at least published, it's vendor specific, but if it is published, then it's okay for the kernel to support it.
Yeah, I mean, it's as long as, I mean, it's basically a, can we point vendor 2 at vendor 1's implementation and say, hey, vendor 2, you're really doing the same thing as vendor 1. Don't invent something new. It's trying. So it's not about in the standard or not. It's about trying to control unconstrained innovation.
Correct.
Unconstrained value add.
Makes sense.
Jason just texted something interesting. He said, could Linux publish a generic protocol that could relay to user space and demand vendors implement it? Is there any chance the boat has sailed on that?
Not totally sure how it would work, given that what you'd be trying to wrap up, given that these could be used for anything. It would be extremely hard to define it cleanly.
Well, I don't know. I mean, I don't want to speak for Jason. I don't know if he wants to unmute and talk, but it sounds like, you know, we could just basically take some blob of data and pass it to the device. The device then decodes that blob and knows what to do with it, and we're really just providing a mailbox on a mailbox, which I don't know. Maybe that's.
So, I mean, my understanding is the spec here is kind of a little too general, maybe. Like you said, you have to do things in a certain order and you have to follow certain rules theoretically. And I'm saying, let's just get rid of the theoretically and say, if you want to plumb to user space, you have to follow these rules, and these rules eliminate the uncertainty so that the kernel can be a reliable transport for your data. Yes, you can't transport everything and you can't do every crazy thing you want to do, but you can do a lot, right? Basically fix the spec retroactively a little bit, at least for this use case.
Yeah, I mean, there's one classic which I've not mentioned in these slides, but DOE has a wonderful definition that says it gives a load of detail on how you implement a query response protocol, and then says, and you may implement anything else you like.
Well, I mean, that's what we can close off and say, if you implement anything else, you don't get user space access. Sorry. I mean, honestly, it sounds like this thing is very misdesigned. If you guys can't even figure out how to share it between kernel and user, that's nuts. That's like a massive spec fail.
I think it's not so much that we can't figure that one out. I think we can. It's just a question of deciding how flexible we want to be with the bits that we don't know, the vendor-defined stuff.
Well, I mean, including the vendor-defined stuff. It should be rigid. Yeah. There shouldn't be an ambiguity.
It's a blob with a head.
I think part of the problem is that the ambiguity, this precision is specified in the protocols and not the DOE spec. So like the CDAT protocol is well defined. The SPDM protocol is well defined. So I think you had that on your slide, Jonathan, about like, do we just provide interfaces for known protocols and not a DOE driver? Basically, we define, here's the CDAT interface, here's the SPDM interface.
I mean, short term, that was definitely my plan, is don't support anything else until we really need it. Because I think that makes sense for the things we have today. And then we kind of evaluate the others as and when. I would like to move on, but Lorenzo, did you have a quick point on that?
Yes, I wanted to ask a question, but I think you will address it shortly. I mean, it's related to even mediating within a given protocol, in particular to CMA, but I think you talk about this in a little while, so I'll wait.
Yeah, not sure I addressed that particular question, but hopefully.
I mean, well, I mean, just briefly, SPDM sessions, they have state machines, and you need to record in a way that the state of those transactions within the protocol itself. So mediating there means keeping track of those state machines within a given session. That's my question. It's not just mediating between different protocols, but also within a protocol in a way. So, but
yes,
yeah.
you would need, you raised a good point there. We would need to prevent, even if we had a user space access, if it was being used for something like SPDM, it's hands off. Don't touch that one, because you're quite right. There's an immense quantity of state going on in SPDM.
Well, there is user space, and as you mentioned something else, I think that's where we should define the entity that mediates access to those mailboxes, in particular for CMA. But I think let's move on. I mean, and we can discuss it later, probably offline.
Absolutely. Okay, so jumping on to SPDM and indeed CMA, but we'll do them this way around because it makes more sense for explaining what's going on. This is the security protocol and data model from DMTF. It defines a bunch of standard messages and the protocol, and indeed all of the state, as Lorenzo just mentioned, for device authentication and indeed mutual authentication. That's an interesting side note that we probably won't go into, but what's mutual authentication useful for in kernel world? Who knows? So if people have ideas on that, it would be good to hear. It allows you to establish secure channels, so you could have nice symmetric encryption. The first bit's done with public key, private key type asymmetric encryption to do authentication. You can do integrity measurement. So has the firmware changed? has the state of the device changed? What that means is sadly implementation defined. So there is an element there of who exactly is going to look after those measurements, but I suspect we won't get anywhere near that today. You can also do things like key management for encryption. It's used over various different transports. So, I mean, one small detail is we'll probably do it as a library, and the initial proposal is definitely to do that, which is capable of being used on different transports. An easy example for the sort of thing you can do with this is USB chargers verify that a phone can cope with higher currents. So that does use mutual authentication. Basically, the charger and the phone have a little chat and establish who each other are, and only then do they crank up the power on the wire so that they don't set fire to your phone. Can also be used for preventing attacks like Thunderclap. This is a DMA sort of fake PCI device doing DMA attack. There's actually a decent description of it in Alex Merkes's talk, which I think was yesterday, on the case for memory segregation. So I won't go into details on that, but you can prevent it as long as you know you're talking to the right device, and SPDM and similar techniques and basically a device attestation can mostly prevent those attacks. Also, there is a whole bunch of stuff around managing what devices are connected to all your servers in a big cloud, and being able to verify those in a secure way to make sure you've got what you expect. CMA, which is a PCI SIG ECN, is the component measurement and authentication ECN. This uses a DOE mailbox, as described earlier, to carry SPDM messages. It does cover a bunch of other transports like MCTP, but at the moment we probably don't care in Linux. It defines a subset of SPDM, which is useful because it reduces the number of protocols that we need to support considerably. What it says is things like the device must support at least this one or this one. So you either have RSA or one of the elliptic key combinations and particular hashes. So it reduces just how much we have to support in kernel to deal with whatever device is plugged in. Obviously, we might later want to put the more secure, fancy new crypto standards on top of it. Leaf certificates have to contain a bunch of information to relate to the device. It's a bit loosely defined, unfortunately, but typically things like serial numbers and vendor IDs so that you can be sure that there isn't an impersonation attack going on where you're sort of forwarding these messages on to another device and getting that to reply. So why does Linux care about this stuff? Given that a lot of the models will assume, like the mobile phone charger one we had a minute ago, that this would be handled by some other entity in the system, be it either firmware or some trusted element or secure element, that sort of thing. A couple of obvious reasons. One, we might be the firmware. So if you're doing something like Linux boot, it's more than possible that you don't have this in any other embedded firmware. This is quite complex stuff. You don't want to be running it in a very early stage of firmware boot. So you might well want to do it in the kernel for that. Runtime hardware state changes are an issue. So we've got hot plug, particularly if you're doing OS native hot plug on PCI, then basically we're the only people who know about it. Resets. So a classic thing for this is actually the next one, out of band firmware updates. So someone's used MCTP, switched to firmware, and then when you next reset, it loads a different firmware. So in those sort of cases, we need to be able to go and query and say, oh, hang on, is the state what we expect it to be? And also virtual machines. So one thing that's interesting in CMA is a VF can have its own CMA DOE instances. Unsurprisingly, they're not meant to be used by anything other than the virtual machine. There's no reason you'd do that. So this allows a VM to do verification of both that it's the device it expects to talk to, but also the state measurements that you can do can include details of how the PF is set up. So if there's things like the PF has debug interfaces, you could definitely have a measurement that reassured you that they weren't turned on, there wasn't a back channel. Even some of the things that are there for migration, if you really don't want the hypervisor knowing what you were up to and being able to read the state out, then you could lock it down, and the device would then report that it was in a state where there was no way for the hypervisor to look at it. The opening question here is this strong enough to justify kernel support? I think so. I'm interested to hear counter views. perhaps not today, because that could get a little deep and we're running low on time. So this one we wanted to talk about a little bit on virtual machine use cases. So if people want to jump in on this, the simple one's kind of obvious, which I mentioned a moment ago. You've got a per VF CMA instance, and we're providing a nice standard way to check that we trust the hardware and the state of the hardware. There is a paravirtualized story here, which is that it can be useful to do particularly measurements of devices that are being used in a virtual machine that don't have a convenient DOE mailbox to do it. So one option for this would be to basically insert a mailbox into what the VM is seeing and allow that to effectively pass through the measurements. Obviously, there's loads of ways we could do that sort of device attestation going into a VM, but perhaps it's convenient to use the fact we already have a standard that is meant to perceive measurement of PCI device state. There has been a little bit of discussion about using this sort of technology for verifying fully emulated devices, so Vfio type devices. Cases where you've got things like the Vfio backend is actually running in a different VM and you're routing it through the hypervisor, and you just want to verify that you're talking to the right person at the end of the line and not the wrong sort of device or someone trying to intercept it. And you can build a secure channel to have those communications without any attacks in the middle. Yeah, that's kind of all I had on this. Did anyone have any sort of suggestions or questions on this topic? Or thoughts on what they were thinking of doing with it? Sorry, Dan.
But CMA doesn't protect against like you can verify the device, but like you could still be in the middle. Like you could have two NVMe devices, one trusted, one not, and they could route the CMA through the good one, and then your very next read or write to the NVMe register is the fake one, right? It's not. You'd have to wrap the entire driver in SPDM messages or something to make the whole thing secure all the time.
Or use a measurement. True? Because you can set up a secure channel that can't be intercepted because it relies on the private keys at either end. You could say you could have your NVMe drive store some hash of what's been going on for the period of time, and then you could do a verification on that. It's a bit messy. I'm not totally sure how this use model works. It's a kind of one that might make sense, and basically I'm fishing for whether anyone's interested in these use cases.
I was going to say that that CXL.cache protocol has a trust me, I can participate in the CPU cache protocol, can't I? And that seems like a perfect place to have a CMA verification to say, do you really want a device that can launch its own vector attacks on everything? And you probably want to verify that first.
Yes, no, absolutely. Okay, so we actually got further than I thought we would. Okay, so here we get into policy. We obviously need a bunch of controls around this. As I mentioned here, I've made no firm proposals yet, and I haven't seen any for what we actually do about this. So there are questions of granularity. Do we have system-wide policy that says basically all PCI devices on this system, obviously this is some years in the future when this is around a little bit more, must successfully conduct a CMA authentication before we're going to allow them to be probed, for drivers to be probed on them. Otherwise, we just don't trust them. Perhaps we tie it up to things like external devices. So we already have firmware descriptions that say this device is on an external port. And we say we're only going to trust external devices, or at least we're only going to make them bus masters and able to do DMA if we've had an exchange and they are who we think they are. It's not totally clear what sort of granularity we want to do this at. One option for this stuff is there are a number of security protections getting added in various places in the kernel against things like Thunderclap, where we might use bounce buffers or carefully segregated memory regions, or indeed driver audits to make sure that we're immune to any attacks based on granularity of the Iommu. So this is where you've got your buffer that you actually wanted to do DMA into, but the Iommu is only protecting a larger area of kernel memory, and potentially there's something of interest in the remaining space. So if we can verify the device, perhaps we can get away with slightly weaker audit requirements depending on what people's security model is. There are specific questions. Anyone do jump in during this. So what do we do if there is no CMA capable DOE instance available? Classes can often support them. So an example of this is CXL Type 3 memory will definitely support the option. Thanks, Lorenzo. But doesn't require it. I guess we're going to have some system policy around that. Someone has decided whether Type 3 memory devices must support the ability to attest that they are who they say they are and take measurements of firmware and things. So chances are we'll just block probe if they don't have that support. Other questions like root certificates. This entire thing is based on certificate chains. If we don't have the relevant root cert, so we haven't inserted the Huawei root certificate because we don't trust Huawei or we don't trust Intel. Just to use two safe options in this one. And then what do we do? Do we just scream loudly and go, root cert isn't here? Or do we point blank refuse to insert them? I mean, I guess if we were allowing the thing without CMA at all to be used, then we probably still have to allow it if we don't have the root certificate, but perhaps that needs a separate policy control. I think the only easy one is verification fails, which is we did have the right root certificate, we went through the whole process, and we got to the end of it and the authentication didn't pass because basically our signed hash was wrong. That would usually imply that someone was attacking the link or we had, well, a bug most likely, or some form of corruption going on. So that one's kind of easy. Any feedback on this stuff or? Nope. Move on.
You had investigated the IMA. IMA has existing cert verification code in the kernel. I didn't see can they support built-in certificates? Can we like ship kernels with certificates, or do you need to always go back to user space to get certificates?
Yes, so IMA allows for a bunch of different ways of inserting certificates. So you can do it inside a blob of memory passed from Vfio. You can do it via an init-RD sort of insertion, which is the only one I've implemented so far, just a proof of concept. Or you can do it by building them into the kernel. But obviously, the issue with that is, I don't know, it'd be an interesting question whether distributions would be willing to build it in. There are certainly embedded cases where individual people are building their own kernels anyway and would indeed insert them. Moving on, certificate management. Now, we can leverage a bunch of stuff that's there for particularly EVM in the kernel and the sort of certification of existing elements of the operating system that exists that's there for trusted boot. That rather conveniently provides us a bunch of tools. So the way I've mapped it at the moment is to have a root keyring into which you can insert your CMA thing, certificates for your root certificates. And those are then checked against the chain that you read back from the device. There is a question here of granularity again. This is not doing anything to say, I've inserted this root certificate and I only trust it on this device over here. It's saying, I trust it for all devices attached to the system. I don't know whether we need that sort of extra granularity. Lorenzo? And there is another question as well, is that at the moment, I'm using a per SPDM instance keyring to deal with the actual certificates. This is kind of a convenience thing rather than anything more, because it allows us to use all of the keychain managements already in the kernel. I'm not sure whether this is a potential problem. It's a slightly odd model because it isn't a bunch of certificates at the same level. It's very much a chain where the thing might return 3 certificates and each signs the next one. But if anyone has any feedback on that, I'd be interested. I'll just flick through what else is here, just as a preview in my last 10 seconds. So there was no way we were going to get to talk about this, but there is a whole bunch of stuff to be resolved around measurement as well. But that's a little way down the line because we need to get the authentication in place first. And I just include at the end references to the RFCs that are out there and specifications, etc. Thank you very much. Any last questions before Lorenzo?
There are questions on the
sorry,
chat,
I've been terrible. Yep.
Jonathan. To be honest, I don't know if you have time to answer them, but I mean, I have a question. We have a look. I mean, but I also have a question for you and Dan. I mean, where do we go from here? I mean, what's the follow-up? How can we work this out? Mailing list or?
I think in the short term. Sorry, Dan, go ahead.
Oh, I was gonna say that the one question I was wondering is like, do we make this part of like another PCI kind of pre-driver functionality, or do we make this a first-class citizen driver with its own device model, and you can add and delete DOE drivers? I think that was the kind of the open that Jonathan and I were tossing back and forth on the mailing list.
That one, and I think the ACPI question, which we can certainly start the conversation more openly on the mailing list with a few proposals, but it may well be something we need to take to a call that we organise for the purpose.
I feel like all this authentication stuff of devices is going to end up everywhere, like PCI, USB, CXL, everything is going to have it in the end. It feels like it wants to be its own kind of piece of code, not too tightly coupled to PCI.
Yes, that's a good point. Yeah, so for the SPDM level, I absolutely agree. I know a number of other buses have said they're adopting that particular specification, and it's based very tightly on USB in the first place. So basically, it is the USB spec with extra stuff.
Can you tie it to the link encryption? Like, can you say I authenticated with SPDM, and then I know that I did the IDE and my link is encrypted and authenticated?
There's a bunch of extra stuff on, it's using SPDM, but there's a bunch of additional stuff you need for IDE to actually poke it into the relevant components.
But you asked earlier, does the kernel need to know IDE? And if they're connected, then I think the answer is yes, because the kernel has to do the authentication with SPDM, and then it has to know that the IDE is authenticated.
There's a subtlety there, which is that the kernel doesn't have to do the authentication with SPDM. We could well have firmware doing it.
Well, then that wasn't the point. I want the kernel to do it because the kernel knows the policy. The kernel has the policy.
Yes, that's certainly true. There is a separation as well, which is technically SPDM when used for IDE is a different PCI DOE protocol to CMA. It includes everything in CMA plus a bunch of other stuff. So there is a kind of expectation that if all you're interested for, or you've got a model where the expectation is someone else is dealing with the encryption, which if you're not doing peer-to-peer because you've got a device where it doesn't make much sense, then you might well have a policy that just says firmware is going to bring it up and keep it running. And yeah, if it's an NVMe drive connected to the host directly.
Why do SPDM in the kernel at all then, if that's the kind of world you're going to live in? Because like, if I want to say I'm running a trusted kernel and the trusted kernel only talks to trusted devices, I can't trust that somebody else went and set up the encryption to my device. It doesn't make any sense.
You'd have to trust your firmware and talk to it.
Well,
I don't. That's not the kind of the trusted computing framework, right?
Yeah,
we don't trust the firmware.
Yeah, I think there's definitely a model where the OS is the center of trust, but I think there's also a model where like where the vendor wants to make sure that somebody's not plugging in something they're not supposed to. But I think that's not Linux's problem. I think the Linux problem is purely kernel authenticated, kernel setup IDE.
I will add, I was being a bit vague with firmware there. In some cases, this is things like the Realm Manager, perhaps in ARM's model, or I can't remember what it's called in AMD's CEV, but there is a very low-level piece of software you have to trust in order to get any of the encrypted VM stuff to work.
I'm sorry, guys. I need to stop you. I mean, I think, Jonathan, it makes sense to follow up shortly in hack rooms and try to see how to make progress on this. I want to thank you very much for your presentation anyway, and I think we can figure it out in today. I mean, now to follow up on this. We have a break now. I mean, we are, I think, overrunning. Let's start again at 35 minutes past the hour with the next presentation, and thank you very much.
Thanks, Lorenzo.
I noticed few people raised hands. Please let me know if there is anything we can do.
Lorenzo, I think people thought that that's how they indicate they are ready, actually by mistake.
Good. Yeah, I suppose so. Shortly, I will give you, I'll upload the presentation, Jakob, and hand over to you. Just a minute.
I almost thought the lower right corner is the raise hand button. Let me find one.
We are ready to restart. You should be able to present, Jakob. So please go ahead whenever you're ready. Thank you very much.
Yeah, thank you. Can you hear me okay?
Yeah.
Okay, thanks. Yeah, thank you. I'm really glad to be here. And the topic I wanted to bring today is about supporting shared virtual addressing in the kernel. And then also implies that how do we want to handle DMA requests with passive inside the kernel. So this is not a kind of a new feature, and it has been there and have VTD support. Been there for a while, but there has quite a bit of issues. And so this is an effort to kind of rewrite or refactor the code such that we address some of the concerns on the mailing list. And but the ultimate goal here is to support DMA. First of all, DMA requests with passive. A lot of devices are coming with passive capability, and also how we want to do shared virtual addressing, basically share page tables between CPU and the Iommu. Just a little bit background, just try to warm up the kind of discussion. I think Will, in the first presentation, is a very similar picture, but mine somehow got messed up when I converted to the PDF format. Sorry about that. I'll fix it later. I just realized that. So basically, we have without shared virtual addressing, without passive, the DMA address versus CPU virtual address has go through a very almost a symmetrical view. On the left hand side, CPU had MMU, and then CPU has its own TLB, and the CPU page tables. On the right hand side, we have the IOMMU, IOTLBs, and the IO page tables in the memory. So everything's separate, and through DMA API, we have IOVA allocated, and also the device can also use physical address to do DMA as well. With this slide, I try to highlight the changes in red when we share the page tables with CPU. So basically, IOMMU and the MMU still have its own TLBs, but CPU page tables are shared. Therefore, mappings are shared, and that enables the device to do virtual address DMA. So that includes both, the user mode, share virtual addressing, and the kernel mode. But this specific discussion I want to have is for the kernel only, because we have some, I guess, special challenges in the kernel, and also for user perspective. If you want to do share virtual address, there's no really other address options. But the kernel, you can have other options. So I wanted to discuss. So what's in the current kernel is that we're leveraging the the SVA library that's mostly intended for user SVM, and then to basically treat the kernel SVM as a special case, and therefore instead of binding binding a device with a process but we have a flag to indicate that we bind to a supervisor, called a supervisor packet or system packet, so that the packet is pointing to the init the kernel mapping. So of course, we also have a lot of special cases for handling kernel, such as we don't handle page fault and no MMU notifier registered. And also there's assumption that we do the DM device driver who use that only use direct map, but there's and also static. But the problem with that, of course, we are exposing the entire kernel mapping at API level. There's no restriction on basically the once you bind with the kernel mapping, the DMA can go to say stack or vmalloc areas. There's no and no even warning, say for unintended error. And another issue is that we don't have a way to synchronize CPU and IOTLBs. So in case that is for the kernel mapping that's dynamic, like vmalloc or sometimes the direct map ADS updates, there's no way to tell the IOMMU that you need to flush IOTLB. And the third issue that was brought up in the mailing list discussion, especially by Jason, was that in the kernel DMA is supposed to use DMA APIs, and but in this case we're kind of diverge the API by using the SVA lib. So in that effort, and this effort is trying to address those concerns. I just posted a patch set about a couple of days ago. It's kind of a last minute thing, but the patches try to address the SVA and the DMA request with PASIT in 03 addressing mode. The first of all is which we can support physical address mode. So in this is the case similar to what we have in DMA Direct, where some devices, like a trusted device, you can, even when IMMU is on, you can bypass IMMU, but this case is on a per packet basis. The second mode is the IOVA mode, which is making the DMA request with packet DMA API compatible. So we have a supervisor packet will be mapped the same way as the device. So a requester ID, which is the default domain. The third proposal, third mode is the KVA mode. It needs a little bit more attention, so I'll focus on this a little more in the next few slides. So in the KVA mode, we try to support basically shared virtual address, shared CPU table in the we also call it fast mode. And another way is for another mode is submode is that we have devices that's not trusted, but still want to use KVA address for DMA. We'll do map on map similar to IOVA. The only difference is that the address is KVA. But we wanted to be able to switch between the two, the fast mode and the strict mode, transparently. In the patch, I proposed basically two APIs, and one API is DMA packet enable. So in this API is intended for so devices who want to use DMA with packet, whether that's a physical mode or IOVA mode or kernel virtual address mode, and to call this and to set up the actual the addressing mode. And this is on a per device basis. So each device could have its own mode, but for each device, the modes are mutually exclusive. The Iommu domain, which we'll touch on later, is that's used for the KVA mode where mapping is still needed on an Iommu domain basis. For KVA mode, I also kind of added a new API that's doing the KVA mapping that used the domain returned by the previous enable API. So basically, it's like it does some sanity checking for the CPU address range, and also there are more potential to change to check as well, to add more sanity check as well. But so far, it's just a sanity checking for the address range. So here I put a link to the patch set.
Hey Jacob, I have a question on this.
Yeah, please.
So how does it look from an endpoint device driver side? Does the endpoint device driver know that the device is in PCI IOVA mode or in PCI KVA mode, or what does the implementation look like on the device driver side?
Device driver who wants to use PASIT, and they would have to make up their decision. Well, they can get it from their own capability, but I would assume the device driver already know what they want. Maybe I missed your point.
My impression is that with KVA, the device driver can just bypass the DMA API and use the virtual addresses as DMA handles, right?
Yes, that's if that's their preference. But of course, they need to pass the enable API to be successful. That's being scrutinized by the.
But that's not portable, right? We can't just bypass all of our portability extractions for DMA. How is the driver going to work on other architectures? That's not how we design things in the kernel. Like, I really don't see where this KVA stuff fits in, or why we need it.
Well, why we need it, it's basically sharing. Why we need to provide a way to share page tables, right? So that provides some security benefit over, say, physical address.
What do you mean? The kernel mapping and the physical mapping are the same, right?
The kernel page table still provides like permissions, things like that. Well, it's not as I guess. I have maybe you can go to the next slide.
Again, that's kind of you're talking about a refinement of bypass in that case. You're talking about a bypass mode or a pass-through mode where instead of just having all physical memory be readable, writable, you have fine-grained page permissions under there, and that's fine, that's great. But why would a driver care about any of this?
It's for performance reasons too, right? Because once we turn on Iommu, just the cost of creating the mapping.
No. We're running the Iommu in bypass mode.
Oh, bypass mode is a pass-through mode completely. You're right.
Right.
Yeah.
But you can't make them. You can't say I'm going to not support bypass mode but allow KVA, because you've broken all of the security guarantees that turning off bypass provided. It doesn't make any sense.
Bypass doesn't provide any security, right, Jason? I'm missing.
Well, that's my point. It doesn't. So,
right.
And neither does KVA.
Well, with KVA, we have, I think Jacob talked about having two different modes, right? One is a strict mode, another one is an SVA mode. So when you put it in the strict mode, it works as if you're DMA mapping and unmapping strictly, like how the second option works.
But that's not KVA. That's just a normal DMA API.
Correct.
Yeah.
It's in my mind, I was thinking more about compatibility. So you can actually check whether the driver is abusing without doing the map or unmap in the first place. And once you've validated it, it's sort of a reference check. Once you've validated the driver, it seems to be doing all the right things. You can put it in the performance mode in production, actually.
But
right?
The performance mode is not secure. It allows unlimited access to the kernel virtual address space. That's not secure by definition.
It's only for trusted device.
Right.
are
And
not
the
open
policy of
to.
trusted devices belongs in the hands of the administrator. It's not a device driver centric thing. The device driver should use the DMA API, and the administrator should decide if the DMA API provides a high performance bypass or not.
Yeah, we could have user input, but also we like we have the for ACPI, we have the secure SATC object that helps to enumerate which device is trusted.
The admin or the policy engine can use that to decide if it runs in performance bypass mode or not. It's not something that should be part of the device driver, and the device driver should not be calling things like KVA APIs that assume an identity map of the kernel API, because it just doesn't work. The device driver needs to be running in DMA mode. It needs to be running on top of the DMA API.
But this provides a way to fail, say, the device driver say, yeah, enable the KVA mode, and it's not trusted, I get failed, or not, allowed by the administrator.
But there's no performance gain to doing this versus the DMA API running in bypass mode, or the DMA API running in KVA mode under the covers.
Right. Bypass mode would be, of course, going physical address would be the fastest. Right?
Jakob, you're really doing a complete layering violation here again. You try to put policy into the device driver, which is the wrong thing to do. The device driver uses a common API, and somebody set the policy, and then this infrastructure can allow bypass or KVA or whatever, somebody who configured that infrastructure and the policy in there to do the right thing. But no, it's wrong to do it in the device driver itself. It's just layering backwards.
So can we...
Device drivers have no access to policy, period.
Right. I think we can probably look at the DMA pass at KVA as a hint from the device driver. The driver says, I would prefer to do this thing, but the kernel policy can dictate whether this is even allowed or not.
There's no point in having a KVA mode in the device driver. Just use the DMA API. There's not a performance hit to using the DMA API properly.
Well, it's still, if you use DMA API, they will have a separate page tables, right? You use
No, that's policy under the DMA API implementation. You can do whatever you want. You can put KVA under there and return just an identity pointer. It doesn't matter. That's what Thomas means when he says that's the policy layer.
Okay,
right.
So you're saying
you call into the DMA API and you get a pointer, and what the property of that pointer is decides the policy in the DMA API, and not so. The hint, even the hint, is completely bogus, because if the policy says no, or if the administrator says I want everything run with KVA because it's so great for whatever reason, it's a policy decision by the administrator, and it has nothing to do in the device driver. The device driver doesn't care about it. It gets a pointer.
Right. I think all you're saying is that, now that makes sense. So what you're saying is that instead of creating this KVA option, just use the IOVA, and based on the policy, it could either match the IOVA is just mapped to the KVA itself, or if it's a full mapping. So that way the API doesn't necessarily change, but the implementation can change underneath for that particular device if the administrator chooses to do that.
Yes.
Right.
The administrator can put a policy in place that for device Woo, the mapping is going to be KVA based, and it returns a pointer. And if he decides it's bypass based, it still returns a pointer.
Right, that's how it works today. If the device struct has a little flag that says the DMA API is running in direct mode, and it just returns the physical address of the given struct page. It's very fast. Like, there's no overhead here. If you want to stick a bypass, or you want to stick a KVA, or you want to stick a full Iommu with invalidate underneath that the DMA API is the place to do it.
Yeah, I thought about this. The only thing is maybe the DMA API today does not support passive, so we need a way to I guess,
That's
extend
what
the
I was
API.
saying in the email thread is you should create a struct device that has the correct information for the DMA API to support passive.
Okay.
And then it can be a proxy for the physical device that has the product. I mean, that's the easiest way to squeeze it into the API we have today. It's all struct device centric. There are probably other options, but that's like a really hacky, easy way.
So so let me try to paraphrase. So we want to basically uh, have a policy that predefine the device, whether it's KVA or bypass, whatever that is transparent to the device driver. So the device driver just call the DMA API, get a pointer, and then whatever that is, it could be KVA or it could be IOVA, but it's policy already predefined, right? And by the same time, but the fact that it needs a passive to do work submission is already implied. It's gonna gonna need a passive, right? Is this
Well, that's
this
what I was saying with
API.
you create the dummy, the DMA API is based on struct device. You pass it in a struct device that has a DMA context associated with it. And today that's only a RID. So if you create a new struct device that's got the RID plus the passive and you encode that in the Iommu data, you pass it into the DMA API, you can make it work. Like it's still very simple. If you're doing the direct map thing, the DMA API does exactly what it does right now. It says you're direct mapping, just return the physical address of the page. Done. Like there's nothing to do there. If you're doing map unmapped, then it goes down into the Iommu driver, and the Iommu driver pulls out the Iommu data from the struct device and sees that it's got a passive associated with it, and it manipulates the correct IO page table.
Yeah, that's actually maybe the next line I have done.
Jason, what you just proposed sounds a lot like the MDev implementation we already have and which we want to make obsolete.
No, this has nothing to do with MDev. This is in kernel DMA.
Right.
Like when I say create a struct device, I mean create a struct device as a handle to use in the DMA API, not something that has a sysfs presence.
Yeah, but okay, but MDev was created as a wrapper around PES IDs, right?
No, MDev is a lifetime model in sysfs for creating Vfio devices. That's all it is. And when Christoph's next series goes in, that will literally be all that it does. All the messing around with the Iommu is deleted.
Okay, so sorry, Jason, I think in the IOVA mode, I mean, the patch that I submitted address what you suggested here. So basically, we map the read plus passive the same way as the read, right? So we get IOVA, and then so you can do DMA requests.
But this is not the DMA API. That's the whole objection. This is some other API. We don't need a whole other API for this. Use the DMA API.
Yeah, we could the DMA API will be the same. I mean, once you have basically both, the supervisor passive and the default passive point to the same default domain, the DMA API just work the same. There's no change in that case, right? That's for IOVA, of course. I thought that was the original suggestion. But for KVA, is that correct? I mean,
I don't know quite what you're talking about. Like,
no, I'm talking about, say, you said the read passive and the read, right? We map the same way. So both use the default DMA domain. And in that case, the DMA API would just work because DMA API works on the default domain, right?
You said default domain. It wouldn't be the default. Well, it would be the domain associated with the struct device. And if you create a struct device for a passive, then the domain is a passive domain that matches the RID plus the passive.
So, okay, so isn't that the same as the aux domain then? I mean, if we have a passive associated with its own domain, is that what you're, but I thought.
Yeah, let's not get too much into the weeds there. You end up with a domain that's associated with a passive that matches RID plus passive. and you can add page tables or add PTEs to it, right? How we name it and how it gets exposed through the Iommu UPA is a different conversation. But that's deep down in the details, right? It's not.
Yeah.
The driver shouldn't see
Giacomo,
any of that.
I should ask you to wrap up, please. So
Yeah.
thank you. I mean, 1 minute or so left. So please, if there is anything, just go ahead and ask. Otherwise, we'll go back to our rooms.
Okay. So I think we need probably an offline conversation. Jason, maybe in the hack room, or I can ping you offline. Sorry, we're running out of time here. Just maybe 1 minute, and to try to highlight kind of the problem we're facing. So disregard the policy issue. So we still have that IOTLB synchronization issue if we want to use CPU page table sharing, right? So we have here I listed a few cases that modifies the direct map, and would that be a reasonable thing to do, to add a kernel MMU notifier for those cases, for limited use cases, and modify the kernel page table? Those cases then affect MMU TLB.
I think you really need to describe what the use case of this is and what the performance properties are. Like adding the invalidations that you'd need to make KVA work are not free. So there better be a good payback for this. And frankly, I don't see what it is.
Yeah, we'll address the performance issue, and we're currently evaluating it, and will be published once we have a solid data. But we see positive results. Yeah, you're right. We definitely want performance benefit. Otherwise, there's no point in doing that compared to ROVA.
How often do you have consecutive kernel virtual addresses that are not physically consecutive to? The only case that I know of that happens is under the VMAP.
But that's still a security advantage. I mean, if we want to do DMA with virtual address compared to physical address, right? I mean, it's both performance and security.
You can get the security without having to pay the performance cost. I could set up an IO page table with sort of a physical address mapping that's sort of granular and more secure than what we have today. I don't need to use KVA to do that. The main thing that KVA gets me is that I get to have the VMAP still be linear in my IOMMU. So I'm struggling to understand where that's a performance win.
Yeah, I think we need to wrap up, and maybe Jason, I can talk to you offline. Yeah.
I think it's an interesting discussion. I fear that it may take longer than a couple of minutes, so I think it makes sense to continue in hack rooms. I mean, so I have to stop you guys. Sorry about that.
Thank you.
No, thank you for presenting and everyone who chimed in. We'll take a short break. I mean, 5 minutes break. Let's rest. I'll try to restart 5 minutes past the hour. So actually, it's 2-minute break. But I mean, let's restart as soon as we can. But let's take a little break anyway. We restart in 5 minutes or so. Thank you. Yeah, Ashok. In the interest of time, I think you should be able to take presenter role and go ahead. I will have to stop you. I will have to stop you at 35 past the hour, so I think we'd better get going. And thank you very much. You can go ahead anytime.
Sounds good. Can you hear me?
Yep.
Okay. Mega, are you around?
Yeah, I'm here.
Okay, so I'll give you a brief intro on today's topic, and then I'll let Mega take over. So basically, when we started working with the IMS framework and things like that, we figured out that we wanted to make some enhancements to how interrupts are being allocated in the device drivers. One of the deficiency was all drivers actually have to allocate everything that they need upfront during probe time, and nothing could be dynamically added or deleted. Of course, this was a limitation with how the legacy MSI worked, but not necessarily a limitation with respect to how MSIX was defined, or for that matter, how IMS will also be defined actually in future. So given that, we also saw that how Vfio was sort of trying to be playing nice in ensuring that a guest will not use a ton of system vectors by allocating them on demand underneath the covers whenever the guest does an unmasking of an IRQ. So even and there were obviously it's drawn into a big hole there because there is no success or fail for the unmask operation itself. It only is present for the allocation of the IRQ. So we kind of trying to back out some of those things and make some changes. So we first obviously started with how we're changing MSIX, for instance, how to dynamically add and remove vectors. And we have a few opens on IMS we can address right after this. Go ahead, Megan.
Yeah.
Ashok, does that, and Mega, does that patch set actually address the current problems of the word stuff, which violates all rules of our interrupt subsystem at once, or is it still based on the same mess?
The proposal that Mega is working on is being able to add vectors after probe time. It does not address the VFIO, deficiencies and pitholes. It made wrong assumptions about how these things work. That will be addressed separately. So this is just for the core part, providing an API to dynamically add and remove vectors. Does it answer your question, Thomas?
Yeah. Yeah, kind of.
Okay, so as Ashok pointed out, we wanted to make the MSI allocation in the kernel much more flexible and dynamic. Currently, each device driver can just ask for how many ever MSIX interrupts that they want upfront during their probe phase. But with the introduction of this new API, we are able to allocate MSIX interrupts even after probe phase. We've introduced this new API called PCI add MSIX IRQ vector. So basically, this API needs to be called only after certain number of MSIX interrupts have already been allocated using other helper APIs like the PCI alloc IRQ vectors or PCI enable MSIX range, etc. So each time this API is called, it only adds one MSIX vector to the device. And if it's successful, it'll return a zero-based device relative interrupt index, which in other words is just the entry number into the MSIX table. So this, whatever is returned could be easily used with the existing PCI API to get the corresponding MSIX interrupt. So this doesn't change anything with the legacy drivers. Legacy drivers can still simply use the existing PCI alloc IRQ vectors API. So did we have any comments on this so far? Okay, so we have the patches ready, and it's ready for submission. And after this talk, most likely I'll be submitting it to upstream. So earlier, I mean, we had this similar patch set around a couple of years back, wherein we had no definite use case at the time, but now with the Vfio use case, we hope that this will find much more speed in the kernel community. So yeah, that's all I had. Ashok, you can carry on.
Okay, so that being said, the two other opens I had for IMS were sort of familiar. The first one is more familiar, I think, to everybody. IMS was sort of defined in a way that allows a bit more flexibility for devices to define or dictate the format of where these messages sit on the device or in memory itself if we need to choose so. Right now, I think the IMS core has prescribed a format, which is exactly what the first implementation of it from DSA actually provides. They're not exactly the same as PCI and the MSIX formats, but they're slightly more optimized for storage on the device itself, right? So that I believe, maybe Jason, you had mentioned that you have certain other devices where the format isn't exactly the same, and how we should define them for future uses.
I don't think the format should be part of the core infrastructure. The format belongs in the device driver. Each device is going to have its own format. Like, I don't expect the next Intel device will reuse the same format that IDXD is using.
Right. So I think that's something to, I think maybe the first implementation would kind of keep what the DSA format is, and it's definitely more valuable for the device driver to actually specify where these formats sit. That's all, actually.
I think it just boils down to where do you put the RQ chip implementation, or what do you call the RQ chip implementation? If the RQ chip implementation is called RQ chip IDXD, then everything makes perfect sense. If you call it RQ chip IMS, and it's kind of weird.
Correct. Exactly. I think that makes sense. With IMS being standardized, we almost make it look like how the PCI MSIX format is, but something different. It's certainly difficult to teach the core every single time. So as we progress along, I believe we will probably make the IMS more of a device-centric format rather than IRQ chip coming from the driver rather than the core itself. Actually, that's certainly a good direction. And I think the next part we had was IMS also, at least for the IDXD driver, has a field that we program in the MSIX permission table because we allow SVM type operations that use the enqueue command to submit from the guest driver itself. And when such submissions happen, the device needs to verify whether the interrupt that's specified in the descriptor is authorized by this VM or not. So in order to make those checks, the device needs to be programmed with a passive entry that belongs to the guest itself. Now, I think the first implementation we spoke about was if every device has a default passive, and if it is stored in struct device, then IMS core can actually program this also because it knows the format on the device, and it also can program the passive when.
But again, you've mixed up things. This is all IDXD special behavior. All of this. Another device might use the passives for different purposes and might not need this security check on the passive, or might not put it in the IMS entry.
Right. No, I understand that. I think this is only if the device driver this is not enforced by the core. This is required by the device driver. So that's how the API works, right? So if you have no definition of user space or a kernel submission that specifies an interrupt handle along with the descriptor, you certainly don't need the passive thing at all, right?
I thought the issue was you needed to make the passive dynamic because the guest is changing it or something.
That is the second part of it. So if we provide something like a mediator device, right, and that is fixed, we already have a passive for it. The core can actually program the pass permission table along with it to make sure that inner VM interrupts don't cross each other's boundary, right? That's the purpose. The issue for number two really comes along when the device, when the driver inside the guest is doing, say, kernel SVM, for instance, and there is a new packet that's allocated, which will be in the guest packet range. That programming happens much later. And that the host driver, the mediator driver, will be the one that actually intercepts that permission programming from the guest itself before it programs the physical device with what the host packet translation should be, right? Which cannot be done by the core. It needs to be done by the driver itself. So if we, if the IMS formats and the programming are completely within the driver, you have that flexibility of switching the packet for the guest when the guest is programming the real packet, which will be different from the default packet for the device. Right? For example, a mediated device can have a packet 1 as the default packet with it that was created, at the time of creation of the device. When the guest is actually trying to do SVM operations, it needs a packet on its own, and that's a guest packet 1. But guest packet 1 is not the physical packet, so you need to intercept in the host driver, convert that guest packet to an equivalent host packet, and it must be programmed in the descriptor for that.
Yeah, but that only works for this particular setup where we actually can trap the access into the IMS.
Right.
But as we discussed before, this is not a general resolution, and it's going to fall flat with anything else. So rather than having yet again a magic interface which just works for IDXD, while we are knowing that IMS needs this for in other scenarios where the storage of the packet is in a totally different place, which is not trappable, why aren't we going right away and do a proper setup of this, that the guest actually requests the or negotiates the passive setup with the hypervisor. I mean, we're going. Can we please not do all these device-specific hacks if we have to solve a general problem? The next driver will have to solve it anyway. So, but then we have drivers which do A, and we have drivers which do B, and we have no consistent interface. Doesn't make sense.
I think your suggestion is, rather than making it a device-specific thing, we probably should use some form of a hypercall or something to negotiate the guest packet directly from the host, and now you know exactly what that packet should be.
Yeah, I mean, you say you need a hypercall or whatever you call it, and say, here I want to use guest packet 5 for device XYZ, and then the host says, okay, I grant you, I don't grant you, or whatever, which also gives you a proper error handling. And then if it grants it, then the host takes care that the host packet, which is or the translated packet, is written to the right place where the host can access it. And that's universal functional for not only for IDXD, it's also functional for all the scenarios Jason described in the email conversation.
I see. So, but the only catch is that this happens much later when the guest is actually programming the IRQ, right? It's not done. It's done much later in the guest driver lifecycle. Right? The binding that packet with the IRQ happens dynamically in the guest. So the hypercall can actually get the translation between the guest and the host packet, but we also need a hypercall to program the IRQ itself with this guest packet in order for the code to properly program it directly, correct?
Probably yes, but that depends. I mean, if the IRQ setup is done is anyway trapping out into the host, and the IRQ is related to a particular device, then the host knows the requested packet already. So I'm not sure whether you need an extra hypercall for that.
Yeah, so I mean, that's the difference, right, Thomas? It's not the default packet. This packet is something different than the device's default packet. So every struct device has a packet, that's good, which we can always figure out. But the guest is now allocating a new packet to use SVM type operations on it.
Yes.
So
the guest allocates guest packet 5, and then because it knows it's a guest, it calls the hypercall and says, "Hey, I want use guest packet 5 for device XYZ."
Right.
So the host or the hypervisor says, "Okay, I know. Oh, this is a device which belongs to the guest, and I'm going to provide a translation." And the host has a device representation of the guest device, right? So it can stick that allocate a packet right there, can stick it into that struct device. And once the interrupt programming happens on the guest, the host knows this is an interrupt associated to this particular device. So I'm not seeing the problem here.
Right. Okay. So we need to trap when the MSIX entry in the guest is being programmed, and then switch it over to at that point. Actually, then that's when the real physical permission table gets programmed. Okay.
Yeah, because at that point, because you did the setup in the right way. So a host requests the passive translation, which a guest requests the translation, which the host grants, and the host associates it to that particular device. Now the guest starts the interrupt, which programs the MSI entry, which traps out into the host, but the host already knows the translation.
Okay.
So,
yeah.
So
and
then,
we will. That makes
so
perfect
then
sense.
So for MSIX, that's completely transparent. It might not be completely transparent for the use case Jason is envisioning, but
well, I'm worried that we're building hypercalls that are really narrow in scope.
Right.
In which way, Jason?
Well, and that they're only usable for IDXD is what I mean.
No, I mean passive translation should be not restricted to IDXD, right?
No, I think what Intel has done with the way they work their IMS and the fact that they have an IMS table, not like dynamic allocation of the vectors, is very much restricted to IDXD. And does the hypercall you're thinking of only work in that world? I'm still kind of struggling. Like,
no, I mean for your use case, you need a passive translation as well, right?
I'm not sure we do. Like the device is much more intelligent. It knows that that there's a VM, and it knows that the VM is restricted to some passage. When the VM goes and asks for an interrupt, the device can make the right decision, I suspect.
And also for passive translation, we have a separate interface via the virtual MMU. Through the Dev MMU framework, we can build that information. Just for passive, we don't need hypercore. But Thomas, earlier you discussed that maybe for guest request RQ, generally we may want a hypercore to make sure that the host side resource can be secured. For that part, maybe we need a hypercore.
Correct.
Right. But for passive itself, I think we already have a mechanism to build all the necessary information based on the new, Dev MMU framework.
I mean, if you can do it by via Iommu and do the passive translation via Iommu or the virtual Iommu, then this is going to end up somewhere in the host as well, right?
Yeah.
And is associated to that particular device, so the host has the information.
Yeah.
Yeah. So I mean, then you don't need a hypercall because you already have the translation and the host already associates through to that path through device. So in the case the interrupt is programmed, it has all information and the guest traps out into the host. The host has all the information. So
yeah, I suppose when guest trying to write the guest to MSIX entry, at that point the information should be already the host side. So when that operation is trapped, then the host IDSC driver should be able to figure out the host passage.
Yeah.
And then we just need a method to net the RQ chip to program that ID to the figure entry. Right.
So what happens? Yeah. So what happens if the guest did not do that Iommu thing translation setup up front before trying to program?
Yeah, it must be done before programming MSIX entry. Right.
Yeah, sure. It must be done before, but what happens if it didn't?
If it didn't, when it writes that entry, the host will say there's no host physical passage. I think that's why I said the hypercore idea still makes sense. You mentioned that when guests are trying to request RQ, there are multiple reasons. Maybe the host cannot satisfy the requirement. Passage is one thing. Another thing is maybe there's no enough IRT entry, right? So generally, we may still need a hypercore to detect such failure in case of host shortage, resource shortage. But just for this, yeah. For that part, I agree with you. You mentioned that earlier.
I mean, yes. I mean, the question is, and we discussed that before, and we never came to a conclusion, is do we want to be robust and polite and let the guest know that a resource is not available, or are we going to end up with just non-functional things, or is the
in the end, I think we will need such mechanism. At least for cooperative guest, it can use this hypercore to know that host not meet its requirement.
Right.
Right.
So, but the hypercall is an orthogonal issue then. If we require the Iommu translation anyway, then
but the hypercore is not for passive, right? The hypercore is still maybe some just for request RQ. For guest request RQ, is need to do a hypercore to make sure that the host have every resource ready, right?
Right.
Didn't we talk about this when we were discussing all this? That Microsoft Azure or Hyper-V had these hypercalls already, and they were just kind of missing from the standard Intel stuff.
This hypercall is the Intel, right? We're just talking about some general mechanism in case the host cannot, get necessary resource. Then guest know it should not enable that.
What I understood is that Hyper-V had a hypercall to set up an MSIX, and that's how they did theirs. But on the kind of the normal KVM side, we do a PCI write to an MSIX vector address and trap it. Right. That one allows you to return an error, and the other doesn't.
Yeah, which
is it okay
which
to use the same one, or maybe we need some? Yeah.
Yeah, and the PCI write to the MSIX entry is I mean it's trapped, and then what's the outcome if the host cannot provide the resources? So the guest will not see an interrupt, but will not see why. So that's what we have right now, which is suboptimal. So Jason, you're saying Hyper-V already has a hypercall for setting that up?
I thought that came up in this long thread. Sorry, it's been a while, so I don't remember exactly.
Yeah,
but I've had that impression.
Yeah.
Yeah, they
I
have
forgot
hypercall
most
to
of it.
get to the yeah.
I
They have
thought that
hypercall
was
to
for
get to
setting the
the
inner
user
remap
data.
entry. Right. I thought that was for the inter remap entry setup, right, Jason? Not necessarily for the PCI MSIX stuff, I thought.
Well, we do the normal case, the KVM case does the internet remap entry setup
Right.
when it traps the MSIX right. And
Right.
you know, what I had inferred is that instead of doing the MSIX right and then trapping it, they did a hypercall and set up the remapping entry and you know whatever else was needed.
Yeah. Which makes sense because it's polite. If the host runs out of resources, it can at least tell the guest, oh no, this is not working.
Well, what I liked particularly about that approach is that it gave an option where you could do a hypercall and say, hypervisor, you know, set up a remapping entry and give me the addr data pair for that remapping entry, and I will program it where it needs to go. So if I'm using MSI, I program it in MSI. If I'm using some IMS thing, I program it in the IMS thing. It no longer the hypervisor no longer has to trap all this stuff.
Right.
Yeah, and in the particular case where you store it in memory, like what your device is going to look like, the hypervisor can't even trap it.
Well, exactly. That's why I like it so much, is that it's clean.
Yeah, and it makes sense even from the robustness side in the guest, because the guest then actually knows that a particular interrupt is not going to come in, because the request IRQ or whatever the mechanism is where we hide this will just fail.
Correct. Yes.
And that makes a lot of sense.
Yep.
And basically you can make that hypercall mandatory for the IDXD PACEIT stuff, and then we can add on it for Jason's requirements to hand back the information he needs to have in the memory.
I think if you make a hypercall that hands back the information you need, then IDXD can be solved by not using MSIX. Like, don't emulate MSIX in the guest. Give it a proper device-specific IMS interface. And you know, if you have to trap it or not, whatever, but you're communicating in a clean way. You can communicate the passage. You can do SVA. You can do all this crazy stuff because you're not restricted by what MSIX gives you.
Right.
Correct.
Ashok, sorry, I need to ask you to wrap it up. So please, if you need, please go ahead.
Right. I think this is good discussion. So we will, probably go back to the drawing board and get the hypercall related things worked out and follow up in the mailing list.
Okay.
That's good. Yeah. Thanks, Thomas. Thanks, Jason.
Can we start a new thread for that? The old one is already unreadable.
It's a stack overflowed already. So let's do a new thread. Thanks, Thomas.
Yeah, thanks.
Lorenzo. Bye-bye.
Thank you, everyone. I mean, we'll take a 10-minute break and start again at 45. Thank you very much. Hey, Kevin, we are about to restart. I'm going to make you a presenter.
Thank you, Norino. Can you hear me?
Yeah.
Okay. Okay, let me start.
You should be in presenter mode now, and you're all ready to go.
Yeah, I get control. Thank you. So today, Paolo and I will introduce the unified I/O page table management for pass-through devices. First, I will give a brief background for the motivation and also some high-level concepts. After that, because this is a involving many tasks, so I also want to spend some time to review the plan, including a list of planned tasks. After that, Paolo will introduce how to manage the security context for pass-through devices. This is one important aspect for user-initiated DMA. After that, based on remaining times, there are several other opens we can further discuss. And yeah, if any questions, just feel free to stop me. So basically, I think the current problem is maybe most of you know that now. Previously, 2 years ago, there is only one pass-through framework in Linux kernel, that's Vfio. And 1 year ago, we also have the VDP, the second one. So now we have two pass-through frameworks, both provide the similar functionality to the user space. And today they have their own IMMU logic to manage the I/O page table. Then that logic is relatively simple, but moving forward, when we talk about some new IMMU features, such as the passage support, listed translation, I/O page fault, etc., if we duplicate those logic in every framework, it doesn't scale. So here, I think the proposal is to have a unified framework, the IMMU, to centrally manage every I/O page table for pass-through devices. And any new feature developed, introduced to this new framework, can be shared by both and VDP. So the user space applications will a unified interface via /dev/IMMU for any related activities. And then the Vfio and the VDP become device driver. They only handle the user access to the device resource. And of course, we also need to support for backward compatibility. So we still need to support the legacy UAPI in VDP and but within Vfio and VDP, their existing IMMU driver will be converted to a shim layer to collect the legacy UAPI to the internal dev IMMU helper functions. So in the end, this is once this framework is ready, in the future, everything related to your DMA will be consolidated in one place. And yeah, and also special thanks to Jason. He initiated this idea and also gave many suggestions for the final framework. And this slide gives some key concepts to help the following discussions. So basically, here we use the Vfio as an example. Basically, the most important context is IMMFD. This is a container for holding multiple I/O address spaces for the user application. After the IOMMU is created by opening the /dev/IMMU, the first step is to build the collection between Vfio and IMMFD. This is by calling the bind operation. So basically, the bind will put the device into a security context. Vfio will make user access to the device is not allowed until the bind is completed. Paolo will talk more about this, how to guarantee this secure access as for the bind. Once the bind completed, the MMFD, each bound device is tracked in the MMFD. This device could be a physical device, could be a MDAV with optional packet, and also at the bind time, the user space can provide a cookie to mark the device when receiving event, such as IO page 4 event from the kernel. After binding is completed, the user space can use the device get info to query the MMU related format and capability information for each device. And then the user space can choose to create IO address space. When an IO address space is created, the user need to specify the format information for the underlying IO page table. The first important thing is where the IO page table is managed. The one is the kernel managed page table that's managed by the IMMU core layer. This is the model and also what the current Vfio provides. In the future, we will also support the user managed IO page table based on listed translation. This is necessary to enable guest shared virtual addressing. And moving forward, there's also other usages, such as to share a page table from another subsystem with MMU. For example, we can share a page table, the MM, with MMU, or even share with the EBT. That's another intended usage. And when this translation is required, this also need to specify what's the parent IO address space information. Once the IO address space is created, the next step is to attach a device to the IO address space. This Vfio will specify which device is attached and also optionally provide the passive information if there are multiple address spaces supported on this device. Based on the attached information, IOMMFD will install the IO page table to the MMU core layer, to the MMU hardware, to activate this IO address space. Then, once everything is established, the last step is to manage the IO address space based on the type. For example, if it's a kernel managed, then just use the Vfio equivalent map on map command, or in the support a user managed page table, it may use the IOTLB invalidation protocol to update the mapping. And also there will be fault handling command between the user and the kernel. Yeah. Basically, this is the key some key concept before we move. Any questions in this slide?
Yeah, one question, Kevin. So when you say user managed, are you referring to the stage 1 translations?
Yes, stage 1.
Okay. Okay, got it.
Yeah.
I think just while we have this slide up, it's maybe I'll share how I kind of view things. This really is shaping up to be a subsystem, not unlike DRM or RDMA, that's really about taking a piece of hardware and allowing user space to talk to it directly or efficiently, very efficiently, without a kernel bypass. Like when we talk about user managed page tables, that's a piece of user space memory that the MMU hardware is going to effectively DMA from and talk to directly. And things like invalidation of the IOTLB. I mean, I'm sure we're going to have approaches that don't need a kernel translation to do that. So I think it's really important to see it in kind of that view. The other half is that it's supposed to provide a very generic interface that things can use to access these features that work on all of our platforms and all of our hardware.
Yes. So that's why this framework is all for the pass-through device, for the user space. For kernel, they still follow the current DMA API, the well-established mechanism. Yeah. So here is a rough task split for all the features we have been discussed so far. Currently, we are working on the basic skeleton, and the first version just sent out in last weekend. We already received many great comments from Jason and Alex, and welcome to take a look. Basically, this skeleton only support Vfio, support only Pci device, and provide Vfio type 1 v2 in equivalent mapping semantics. Once this skeleton is completed, the tasks can be split into several categories. Most of them can be worked on in parallel. And the first one is to move the remaining Vfio devices to Vfio, including the software MDAV, including devices on PowerPC platform, the platform device, and also a special group, category that's for device want non-SOUP DMA. This requires a special contract with KVM for at least for inter-platform. I'm still discussing with Jason about whether this will apply to other architecture. Yeah. After all the device types are moved, then we can convert the IMMU type 1 driver into a CM driver. That's the last step. This is completed. Vfio will always use this new framework. Yeah. And here there's one open I want to discuss here is before we create, make the type 1 as a CM layer. Actually, there's within this transition phase, we have two drivers, both providing the same semantics. One is the Vfio type 1, one is this, MMFD within MMFD. So definitely we don't want to duplicate code because the related code is more than 2,000 lines of code. So, but I'm curious, whether any suggestion how we want to share it. Do we want to keep the type 1 driver and then have MMFD to call into the Vfio, or we just move code to MMFD and have Vfio to call the MMFD, or just put it in another place out of both, directory? Yeah, I'm not sure. Yeah.
I'm hoping there are various fixes and improvements that you would make to the type 1 code that would make it easier to re-implement it in the dev Iommu code so that we just stop using it over time. So we would have some period where there's duplicated code, but I'm a little afraid of just ripping it out and using it as is, that it's going to stay as broken as it currently is.
So does it make sense that we first split the mapping related logic out of into a new file under Vfio, and then when we add MMFD, we just move this file to MMFD. Would that make this transition simpler?
Well, I would see maybe two possible endgames here. One is that it's kind of what you suggest, maybe that the VFIO code is just a shim. So when we get a VFIO ioctl, it translates it to an internal IOMMUFD ioctl effectively. That has some nice properties, right? It gives us just one data type in the kernel. Everything's kind of very, very simple. Another endgame would be where we basically take out the data structure that's holding the software page table and synchronizing it with the domain and put that in like some kind of library, and the two things consume it. In this case, we don't end up with one data structure, or we don't end up with one IO page table object in the kernel. We still have the VFIO version of it, and we still have the IO version.
Yeah, for the first option, if we make the shim at the current state, we need to solve make all those device types move to use MMFD, right? That may make the skeleton require more time. We're blocking other tasks. So maybe I prefer to still do the, as you said.
Well, this is why I said end game, right? The end game. Where do we want to end up? Right. So how do we get there is a slightly different question. So if you can see a technical solution where the end game is we only have IOMMUFD, and inside the kernel there's some thin translation layer, that guides, I think, how we get there. But if you say, there's some reason why I can't do that, some weird thing about the Vfio API that we just can't shim, maybe we don't even try.
Yeah, okay. That's I know your point. And also, and we will think about this one. Yeah. So this is first category. The second one is definitely just to move VDPA to also use the new MMA. The next one is there will be some new device types, right? The most important one might be hardware MDev or subdev with passive support. Another important category is user managed page table. For this one, basically there are 3 subtypes. One is to support the nested translation, iOS nesting. Second is passive virtualization at the IO page fault. Of course, for passive virtualization, naturally, just based on latest discussion with Jason, this one should only apply to the virtualization case with VMMU. If we talk about the Eurospace driver, there's no need of passive virtualization. We may need another mechanism to manage the passive just within the kernel. That's another task we will need to add. And for passive virtualization, based on different vendor, it's also difference for ARM AMD and also for Intel with include command and without include command. I don't want to expand those details, but those are some further tasks we need to develop. The last category is the catch-all category for all miscellaneous tasks that people have been discussed before. Is the software listing. If we don't have hardware listing, but we may still implement software listing, this can still allow us to do the centralized accounting of locked pages. The second one is IO page fault. Some people already actually have some patch for Vfio to do on-demand paging just in the kernel, but it's also blocked. After the new skeleton is ready, this effort can be revised. Another one is, for example, some vendors now support the IMMU hardware 30-bit. This can be also integrated with the migration flow. And talk about the shared IO page table. And the last one is, just in the KVM forum, AMD actually support the hardware-assisted virtual MMU. Suppose this framework should be fit for them to further extend. So anyway, it's a long list. And I think in the end, you don't need the community collaboration. Many tasks can be done in parallel. So we really look forward, to the collaboration in the community to accelerate this progress once the skeleton is finished. Currently, our full time is still spent on the skeleton. We hope this can be, as early as possible, and then other tasks can be started earlier. Yeah. And there's some questions in chat. Yeah, please go.
Yeah, regarding the collaboration, is there any alias or anything like where people can reach out if they want to contribute and help with some of the tasks?
Yeah, we can just discuss in mailing list, right? If you are interested in any task, you just send a mail, then just work on that.
Okay.
Yeah. Okay.
Hey, Kevin. I have a question regarding the hardware assist of the IMMU, and could you explain a little bit about that? I mean, just briefly.
Yeah, it's sort of you may saw that presentation from AMD, right? They actually can assign. They sort of like a SR. They have the virtual function VMMU in hardware. You can assign the VMMU to a guest, so you don't need to trap the invalidation request, right? Some acceleration from the hardware.
Mm-hmm. So does it sound like we're going to expand the IMMU FD to support such feature in?
Honestly speaking, I haven't think about how to extend MMFD for this task. That's just one new item I realized recently. But yeah, maybe we can discuss offline. We still have some other open spots to discuss here.
Okay.
Is that okay?
Okay.
Yeah. You can say it's a non list. For every task, there may be some design open, we can spend lots of time. Yeah. Okay, so the next one I will give to my colleague Baolu. I will introduce how to manage the user initiates DMA.
Okay, thank you, Kevin. So, for a pass-through device, we needed to build a secure context. Once the device is assigned to the user access, so the secure context should be kept until the device is returned by the user to the kernel. So first, so we define the secure context as the user initiated DMA can only comes to the process memory or the devices in the same group. And also we need to guarantee the exclusive DMA ownership on the group. So device in the group must be bound to the owner driver or the driver that is DMA safe or it is driverless. So actually, for Iommu FD design, we can copy what the Vfio does today, but there's one exception. So for Iommu FD, we needed to manage the secure context switch during the device is managed by the user level. For example, a device could switch IO address space to another one. So during runtime. So currently Iommu API has a problem on this transition because where a domain is detached from a device, the default domain will be reattached. So this is for with Vfio design. So but it's not it doesn't work for our Iommu FD case. So our idea is to develop the user initiated DMA secure context in the Iommu core, so that the upper layers, for example, the Vfio, IMMFT, or even other VDPA framework, can use the common code for the secure context management. Kevin, can you yeah, the next page. So our proposal is we can we must first we must define a API for the upper layer to tell the Iommu core that a device is going to assign to the user. So the secure context should be set up. So this API is called the Iommu device initiated user DMA. So on this slide, we just show the device centric APIs, but we could also work out the group centric APIs so that the Vfio which is group centric could also use this API. So here we just use the device centric API as an example. So when the device bind to Iommu FD, so this interface will be used by the upper layer to tell Iommu core that we should put the device and and its Iommu group into a secure context. And during runtime, so the upper layer could use the attached device, detached device, or attached group, or detached group to switch between different secure context. Yeah. So once the user completes to call the last API Iommu device exists user DMA to tell the Iommu core that the secure context is end. So the Iommu core will do some cleanup work and also reattach the default domain to the group so that the kernel driver could use the device for kernel DMA. Yeah, that is our proposal.
Hey, Baulu.
Yeah, hi, yo.
Hey, so the way it works today is that Iommu attached device only works on devices which are in their own group. So they are the only device in their group. Otherwise, you have to use Iommu attached group, I think. So the dance with the ref count is probably not necessary, right? Or do I miss anything?
So
the ref count is the ref count is acting as a lock, right?
Yeah. Actually, that's a question, Jorg, we want to ask you, right? Several years ago, you added, you actually changed the attached device to only work for group with one device. Is there any reason? Currently, we just extended the reference count only for, but it still keeps the original logic. Yeah.
The reason is that we have Iommu groups, and for Iommu groups, we need to make sure that every device is attached to the same domain, right?
Yeah,
well,
but
no,
so
that's too strict.
It doesn't make sense.
They don't need to be attached to the same domain. They just need to be attached to the same security zone, security area.
Yeah, it depends on the definition of the group. So the group was defined as a group of devices where the Iommu can't differentiate between, right?
In that case, yeah, then the group is the thing that's attached to. But
and
there's
the
the other
group
definition. That's not true.
Yeah, there's the other definition where you say that the devices are not really isolated between each other. So if you want to lift that requirement, if you want to lift the requirement that every device in the group has been in its own domain, in the same domain, then we might need to split the group concept into this is a group of devices which the Iommu can't differentiate between, and this is a group of devices which the Iommu can differentiate between, but which are not isolated between each other. So
currently we lift this restriction only if the group is marked as user DMA. That means it's already called with this API. So for the normal group, they are still follow your original restriction. Because once we have this extension in place, MFT can be fully device-centric. It doesn't need to maintain any logic, right? They can greatly simplify the implementation there.
It still needs to know about the thing that the first thing Jorg was talking about, where the Iommu cannot match a device. It just can't. The hardware can't do it.
Sorry, just I didn't get.
There's still the case where the hardware cannot discriminate between devices and groups. Like it physically cannot give you different IO page tables for different devices. And we need to manage that in some way.
Yeah, for that we just have detection within attached device, right? If you want to attach devices to different domain, then the second attach will fail. But we don't need to,
Well, no.
detect that.
I think the way. No, I mean, I think the way I was thinking of handling this is you can still attach an IO page table to a device, but the low-level code now says if that device is aliased with another device in terms of what IO page tables it can match, the attachment will fail if it's not attaching the same IO page table. That gives user space a lot of flexibility in how to use this and doesn't force us to make a very group-centric interface for this edge case.
Yeah, that might be a case. And at this stage, we choose a simple way. So we just allow the a single domain for the devices in IMU group. So if we want to support multiple domains for IMU group, maybe we will fix such issues.
I mean, that makes sense as a starting point, and kind of keep it the way I said, where the first device to attach sets the domain for the group, and then all the other devices have to follow. And if we can do better later, then we can further relax it.
Yes,
yeah.
yes, I agree.
But there might be some hardware limitations. For example, the PCI allies. So for that, we maybe need to fill if the devices which are allied for PCI SID, we must force the use of a same IMU domain.
Yeah, that's what I said.
Yeah, in that case, maybe we can have some subgroup concept, right? Only when hardware allows, we can have some subgroup within the group. But anyway, that's a future extension.
Yeah, so when I think about PCI, then the groups which are, or the devices which are grouped together because they are not isolated between each other. There are two cases, which is subfunctions of a PCIe device and devices which are not behind an ACS capable bridge or where ACS is not enabled. So if for standard IOMMU groups we lift the requirement about the ACS and move that into say Vfio groups or IOMUFD groups or whatever we call it, that would split it up and move that that complexity out of the IOMMU core into the layers who actually care about this. Would that be an idea?
Yeah, I think that's the way to go. And I wanted to ask, does anyone use this today? Like, can this even be accessed? If I had a non-ACS capable switch, could I assign two different IO page tables to devices? Two different devices on here.
As the code is implemented today, no, this doesn't work.
So what we're really talking about here is adding more functionality, and that can go later.
Annex has an offstream patch to lift the ACS restriction, but not upstream.
That was entirely a hack that is overused by people in the community.
But I mean, if we don't have a use case for it, it doesn't have to really block things. We just need to get things to where they kind of are today. And if today is one IO page table per IOMMU group, then that's where we need to get get things, equivalent and moving forward.
Yeah, we can follow this state. So there's a real demand. Okay, if no more question about this slide, then the last one is some other opens related to current implementation. For the first one, I already have some discussion with Jason, but want to have a broader alignment here. Now I think there's the main problem is there's a naming conflict, right? Earlier we said that we use IOACID to describe the FD local software handles to represent the IO address space. But within kernel now, there is actually IOACID also used to represent the hardware address space ID, such as Pci substream ID. So just wonder how we want to better differentiate them in this case. Yeah, earlier Jason said that we can use IOACID underscore ID for software handle and continue to use IOACID for the hardware handle. I'm not sure whether others also agree that there's no confusion with this. Yeah.
I think the IOAS underscore ID, if you do it that way, then it's restricted to the IOMMUFD.c file, and it's only used as an input to an X-array lookup. So it's extremely constrained.
But once we start to support PACID, right? PACID is allocated with some IOACID underscore alloc function from this file. cause some confusion.
Well, it's IO-ACID without the underscore, so it's, I mean, it's not a perfect disambiguation, but it is where we are.
Yeah, but we can follow this one if if no other option from other people. Yeah, just quick brainstorming here. Yeah, if no more comments, maybe we can settle it in the mail discussion in case people have other idea after this meeting. The second open is already also related to the name, right? Currently, we call this feature as IMMFD. I think it's not anything opened with FD can be opened with FD with a DV node, such as Vfio is virtual function IO. That's the abbreviation. But how to call this feature? And we happen to say that 10 years ago, before Vfio has a container, actually there is they call that as a UMMU, and use dev/u. I'm not sure whether you guys think the netter one might be a bit for this feature or any other options.
I think Iommu is totally fine because when it's a device file, this implies it's a user space interface, so you don't need to express it in the name again. So diff Iommu is fine with me.
I like it.
You mean
too.
the former, the former one?
Yeah.
Then, for example, within the kernel, the kconfig, how do we want to call this feature?
There's a long history in the kernel of calling things something FD, like timer FD, event FD, right?
Okay, so
IOU ring FD.
So you think
the
IMFD
kconfig
should
is
be
fine. Yeah, I wouldn't
okay.
overthink it.
Okay. The third one is the hierarchy. I think for this one, we already get a good suggestion from Jason. Earlier in current, if you see our V1 patch, actually we just put the device name from any bus just in the same directory. But this actually potentially can cause the conflict. And Jason suggested that maybe we can just create a dummy node called device 0, device 1, device 2, and then link this node to the CSFS path for this device. Then for the user space such as Qmu, it can check the CSFS path and then identify which node under dev Wi-Fi devices should be used. And this is current thinking that we thought that that's a good model, but just in case anyone has different thinking for this one, or Jason, you may want to elaborate if I didn't describe it clearly.
Oh, I just suggested just using integers. Like we don't actually need to encode the bus information here. It's already available through SysFS.
Okay, so all those are quick points to close. Maybe the last one is, finally, do we want to build MMUFD as a separate module? And also, do we want to place this within the drivers / MMU and move it out of there? Do you have an idea?
Yeah, I think there's no reason I think there's no reason it could not be a module, right? A separate module which is then used by Vfio and BDPA.
Yeah.
So I think that makes most sense.
Sorry, which makes more sense?
Having it as a separate module.
Okay. So and also move out of the MMU subsystem, put it in a new tree, or
I would put it as a subdirectory.
Yeah, right. Drivers IMUFD or something. Yeah, but make it compatible as a module. So because all the users are modules too, and if someone don't want to use it, then it just doesn't load the module. So that it's just loaded as a dependency for other modules.
Right. It's a pretty long-standing tradition to keep user interfaces in their own modules. That way, if for security reasons, some system doesn't want to have that UAPI exposure, they can just not load the module.
Okay, gotcha.
Okay, just one open. So if we build it as a separated module, so for example, when Vfio want to call some helpers in the IMFD, So maybe it will use use something like the get symbol to check whether the module has been loaded. So will that be a problem?
Shouldn't normal module dependencies handle that? I don't know. You'd have to point us at a specific instance where we actually need to check for a symbol.
Yeah. Yeah, you should rely on normal module dependencies as much as possible. Like, don't do symbol get things, and don't worry about it. That's what they're for. If you call IMMUFD stuff from Vfio, that's perfectly fine.
Right, with this interface, VFI will become dependent on FT loaded, so it's not the same dependency that we were trying to work around between, for instance, VFIO and KVM.
Right. I never really liked that that weird coupling with KVM, but yeah, I would advise against it here.
Kevin, Lou, I think you have 3 minutes left in this session. Please, if there is anything else you want to discuss, please go ahead. I mean, try to wrap it up shortly. Thank you.
Yeah, I think we have finished the opens. So Jason, do you have anything you want to quick discuss based on the current review status?
I thought I thought it showed that the approach could look really clean in code for the most part, right? Like there was nothing. It's a shame we didn't see how the moving the type 1 code would look, but I think I'm willing to believe that there's a way to do that nicely. And I think it really suggested that the first series should be lowering the group interlock logic out of VFIO and putting it in the Iommu core properly, and then deleting all of that, the sort of supporting code that's all over the place for that. I know Christoph had taken an attempt at deleting it, and it didn't work out because he didn't have a solution for the bug on. But I think we can get rid of the bug on, which will make everybody happier, and then just delete all of it.
Okay.
And that's
yeah, we
like
will
a great
work on that
starting
as the
series.
first task. It then resumes the skeleton. Yeah.
And yeah, making the VFIO into a struct device is pretty straightforward. I'll send you something of what that's supposed to look like. I noticed that you copied the group code to do what you did, and I went and sat down and cleaned up the group code yesterday. So there's something
that
to
will
look
be
at.
very helpful. Okay. Okay. Thank you, Jason. So Lauren, I think I'm finished. Well, yeah.
Thank you very much, Kevin and Lou, for the very interesting discussion. I mean, looking forward to following it up on my list. I think we have coming up a 5-minute break. We start again 35 past the hour with the last presentation from Ashok on opens on PCI, Linux PCI features. Sorry guys for the poll. I'm a bit biased. So Ashok, I'm handing over to you for the last topic of this presentation, of this session, sorry, of the MC. I'll make you a presenter now, so we should be all set.
Right. Thanks, Lorenzo.
It's over to you. Thank you very much.
All right. It's always nervous being the last topic of the day. It's between me and the weekend hitting us. So I'll try to wrap this up as soon as possible. So I didn't have a big list of presentation or anything for this one. Just want to kind of bring up some of the issues that I think exist on the Linux PCI, handling of certain things. And just want to kind of have an open discussion on some of these topics and maybe pick up the ones of high priority or more interest for working it through the mailing list as we go along. So the first one on my list was how we handle MPS today. And the key issue that I had in mind was when we have a device that's through the hierarchy and we know that the maximum MPS between the root port and the endpoint is identified, the kernel can set up the largest setting for MPS through the path for the maximum for the best performance, right? But when a new device gets inserted in the same hierarchy that isn't capable of the maximum MPS that was configured for the path, I'm not too sure if we in Linux actually do this correctly, or even if we do anything at all actually at the moment. That was one of the issues I was thinking, if there needs to be more robust handling of devices that are hot plugged from an MPS perspective. Bjorn, if you're there, or I don't know if anybody else is there on the hot plug PCI side.
Yeah, I'm here. I don't have a good answer for you. I mean, this is definitely a problem area, and I would welcome some cleanup in this. It's kind of a mess currently because I think we configure this after we enumerate all the devices, so it's not a per device enumeration sort of thing.
Right.
And it's intertwined with MRRS as well. So
correct.
Yeah, it definitely needs work.
Yeah, I think the easiest handling we can probably do is if the device is less than what is already configured in the path, we could at least at a minimum maybe fail its hot plug stuff. Or I'm not sure about what the spec says, but if we set the MRRS and the MPS at the lowest level, I believe the root port is supposed to honor that actually, and maybe it'll be compatible actually without necessarily failing the entire path. reconfiguring the whole thing becomes really messy because we need to quest all the devices and stop everything and restart everything. And that might also drop the performance on other already previously attached hierarchy that has a higher MPS setting. So
right.
Yeah, doing something. Go ahead.
So there's, you mentioned questing all the devices, which is true. That I think would have to be done to reconfigure the hierarchy. That's, I think, the what do you call it? The bar reassignment work that was posted a year and a half ago, I think has similar functionality. So there's possibly some overlap with that, but that hasn't really gone anywhere yet.
Right. Yeah, I think, and if it's not compatible, we can always punish the low performing device and say, I'm not able to hot plug because, the current settings are not compatible actually. They might need to go through reboot or fix it in the next cycle to just
Right.
to minimum damage actually.
Yeah, I would think that probably we would want to enumerate the device, but just prevent a driver from binding to it, so that you could still
Right.
look at it via LSPCI and whatnot.
Exactly. I think that's the first, poor man's solution. Then we can improve it as we go along. The next one is more interesting, and I'm not 100% familiar with the topic yet. But one of the issues was that when we take things from the 5-bit default tagging to 8-bit and then extend it back to 10-bit. The impression that I had was that once you have configured the path, it has the same property as what we do for MPS. But when extended tagging is enabled, and if the device is not compatible with that extended tag, I wasn't sure if even probe actually works or not, or if that will result in completion timeouts. I was under the impression that maybe the spec would only dictate that for data transactions and for normal config cycles, limited to the default, smaller sized one for compatibility. But it seems like the spec is not necessarily stated that way. So this is, at least in the MPS side, we can punish the new hot added device. But I'm not sure if there are any ideas about how to treat extended tagging. I think Linux doesn't today care about the 10-bit tag yet. I think the only thing we do is the 8-bit tag, which is just enabling the extended tagging capability. The 10-bit has its own opt-in, which I believe nobody has enabled it yet. I think there are some
There's some patches in the list for that.
Oh, okay.
So, and that's been posted for a while, so there's a good chance we'll be able to merge it this cycle, I would think.
Excellent. Okay, and I think I'm assuming that then it wouldn't still have any handling for the hot added device case actually when it is not supporting the enhanced tagging that you've enabled now throughout the path.
Yeah, I don't know. I'd have to look at the spec again. I thought that it was defined in such a way that, well, I don't know.
Okay.
Yeah, we'd have to explore that some more.
All right. And Linux also today for TC-VC mapping, I believe the only thing we do is we just save and restore during normal suspend resume operations. We don't necessarily manage that mapping in the kernel space. Typically, I think the BIOS sets things up and we just keep it the same during state save operations. Is there should we actually do more about what the kernel does in trying to manage the mapping itself, actually more so than not depending on the BIOS itself for this? I hear crickets. So,
yeah, that's because I'm looking up what TC and VC are. So obviously, I have no answer for you.
There are very few devices that have VCs at all. I mean, there might be some out there, but it's certainly very rare.
Right, right.
I was thinking about Jonathan for CXL, if it has some implications, but I cannot remember off the top of my head.
Not that we can talk about. One of those.
The save and restore of these came about because of GPUs mostly and the firmware settings for that, but I have no idea how you decide what channel mappings to use.
Yeah, CCIX used to use them a lot, but nothing's quite got upstream for that. That would not be BIOS set up anyway.
I see. I think the default mapping is mandatory. If it exists, then the TC0 to VC0 mapping is always there. But how we handle the non-zero mappings, if more than one TC is available, is something that we might need to enlighten. But I think the question is like, how do we do that? Maybe getting a good device example from any of the device vendors that need that thing would be useful, actually. The next one I had was the flattening portal bridge. Apparently, I heard that at least the new Tiger Lake systems are capable of using this feature. It kind of makes a lot of the resource assignments a lot easily manageable from the OS side by not requiring to pre-allocate all the bus numbers and also the memory space requirements. I'm not sure if I have, maybe I missed it actually. No, Bjorn, have you seen any patches or any support for FPB at all actually on Linux yet?
No, I haven't. Not that I remember anyway.
Okay. Other operating systems apparently support this, is what I hear actually, but I have not heard any request from device vendors either, but this is an upcoming topic, at least starting the new Tiger Lake platforms, and possibly will drop into servers to actually mostly on devices that support Thunderbolt and other things where your fan out is increasing. In the past, actually, all the pre-reserved bus numbers for routing is extremely limiting a hot plug aspect. So FPV was supposed to alleviate that, so you can have non-contiguous ranges and still be able to route them through by dynamically managing that routing ID from the OS side, actually. Last
So
one is sort of, yeah, go ahead.
Partly solving the resource rebalancing issues. And one of the reasons that we haven't really gone anywhere with that is that there's not been a lot of demand for it. I mean, I don't see Bugzillas, I don't see requests from distros, whatnot. So, I think FPB seems like it's sort of in the same situation. It's a solution for sure, but it's not clear that we have the problem that it solves yet.
Right. I think the target was, devices like Thunderbolt where you can have, expansions showing up really fast and the scale out happening. And by pre-reserving them, you kind of prevent that capability. I know that at least the host side actually has this capability. I don't know about any discrete PCI switches or even built-in switches that actually support that capability yet. Maybe that's why there is not a big request actually for it.
It's definitely a potential problem. It's just that I don't see the evidence in terms of people complaining about the problem yet. So that would help to motivate either FPV or the rebalancing patches.
Correct.
Are we going to have a potential problem if a BIOS is set up FPV and we then look at it and have no idea what's going on?
What was it, Jonathan? I didn't catch that.
If we've got a BIOS as pre-enumerated stuff and decided to use the flattening stuff, are we going to ignore it? I've been sort of vaguely wondering what on earth happens.
Well, the BIOS setup for the default one is different, but when you hard add it, you need to add the new resource into that into the FPB config space to make sure that they can now route for the new device, right? That's where the OS part comes in. Even though it can be pre-configured, but that's not solving the hot plug issue. The last one I know Linux has some solution for resizable bars today, which obviously all the graphics devices use. But but it's a request from the device driver to say, hey, no, can you do this thing? I think obviously the number of users are very limited, I guess, just only in the graphics community at the moment. But I wasn't sure if this is motivation to actually, remove that requirement from the device driver calling for it versus the PCI core, being able to manage and support the resizable bar stuff.
So what are you thinking there? We would just resize it to as big as we have space for, or?
Yes. Yeah, I think that's always the best for performance reasons, right? So if we can find that the root port is able to accommodate that size, although the default bar size may be smaller because that's what the card comes up with for compatibility, we could provide out-of-box solution by just finding the maximum supported one, and if we have room, let's go fix it up during the probe time itself and resize the bar.
The devices I've seen supporting this put that they support everything in the supported bar sizes. So you're going to be enabling petabyte bars for no reason.
But wouldn't it be the same? I mean, the device, okay.
I think there's currently a driver dependency there that the driver knows what the device can actually make use of.
I see that. Okay. So if the driver thinks that even though he supports petabyte, but if 8 meg is good enough, he would probably just stick with that rather than.
Right. For a GPU, they'll boot with 256 meg bars for compatibility, but they might only go up to the RAM size that's installed on that particular SKU of the device.
Makes sense. Okay, I think in that case, it probably is best the way it is right now. So let's put the request of the driver to actually choose the right size. That makes sense.
Another issue with the current solution is that these GPUs that want a big bar, frequently the post bridge description does not expose a window that's big enough. So I think the drivers do some fiddling with the some processor specific configuration, or to find out what's available or to reconfigure it or something. So it's outside the ACPI description of the windows. And
right, I think you're right. So if the configuration is not correctly done in the root port, there is nothing the OS can even do to go resize it. So there needs to be some out-of-band mechanism to actually tell the BIOS or the system agent to say, like, go make this bigger, and then on the next reboot, things are now rightly sized.
I think BIOS is like avoid windows that cross the 4 gig boundary, and there's missing support in terms of we don't have a way to resize those windows. We don't support SRS on host bridge windows, for instance. So there's I think a few things there that are complicating factors.
That's what I've wished to see on that, is some sort of way to ask the PCI subsystem to allocate larger windows for specific devices when the BIOS doesn't support resizable bars, and then the driver is just stuck.
Yep. And we also discussed it in the platform sense. If for one of the RAS features we worked on in the past, there was a way to communicate. For instance, only certain address ranges are mirrored, for instance, in the system, and we had a way for the kernel to actually tell the BIOS saying, I want you to put X percentage of memory in a mirrored range. If there is some facility like that, we could at least instruct the BIOS and say, go do this on the next reboot, and then when you reboot and come back up, you can check what the size is, and now you might be at the right size, if the BIOS supported that API. Other than that, I think it's just a manual game that the administrator needs to play to make sure that this is correctly set before it can proceed. Makes sense. Okay.
If my previous statement about the device exposing all sorts of bar sizes is true, then BIOSes might have the same issue that Linux does in automatically enabling it. They need device-specific support to know what size to create those windows. So we might see aperture size problems all sorts of places unless the vendor has specifically qualified that GPU on that system.
Correct. I think the BIOS needs to be, aware of support for what kind of cards and what size it is based on its memory, and that might need to happen within the BIOS, pre-configure space before they can do. There's very little I think the OS can actually do to make this smoother. Actually, yep, makes sense. Those are the topics I had. I have some patches for the MPS handling part, and I'll try to take a look at that, and also look at the 10-bit tagging that that Bjorn mentioned actually also offline. Anything else that people see in the PCI space that we need to focus on?
I'm not sure it's something we can really address in any detail, but I have had a few requests recently for kernel folks to get a bit more involved earlier in PCI, adding stuff to the spec.
Right.
So beyond encouraging people to do so, I don't know if there's any other actions we could take.
Yeah, we try to do that at least. In some of the specs, at least, I think Ben has been involved in trying to create some few new models and creating that whole infrastructure before the spec is done. Otherwise, PCI always has the audacity to go create the spec before an implementation, and then we are stuck with something that's not workable for a long time.
Yeah, I mean, all of the restrictions on talking about it do make it awfully hard to collaborate on this stuff. And as you say, yeah, Ben's work's been great for CXL. I mean, yeah, my vision long term is that we implement everything before the spec's published, but in emulation at least. But we can't talk about it in public.
Exactly, that's the limiting factor. With that, the spec development is not in open, so you have to be hush hush, and there's only little people can do with closed settings. So
no,
I wish we could open it up. Yeah.
I mean, it may be as simple as we look for an avenue to at least agree amongst those who are active that someone looks at a given chunk of the spec, even if we haven't got time to go in detail.
Sounds good. Otherwise, I don't have any other open topics, Lorenzo.
Any last minute request for people in this conference while we all are in the same virtual room?
I didn't decide to show myself up because I'm completely dressed in COVID attire.
So
thanks, Lorenzo, for doing this. I think this has been a great conference. Thank you.
It was very interesting, all of the topics, and thank you very much for presenting. Yes, so I think it went really fast, at least for me. To wrap it up, well, first of all, I want to thank everybody who helped organizing it. Krzysztof for the logistics and everything he did, and Alex, Bjorn, and Jörg for agreeing to have this, having this MC again this year, which was very interesting in my opinion, very productive. So I really encourage everyone to follow up discussions on in hacker rooms. I mean, there are topics that I'm obviously involved with, but I mean the others as well. I mean, to encourage discussion on mailing list and patch set. I think I want to thank all the presenters for giving very nice presentations and explaining the problems they are solving very well. And to wrap it up, I really wish next year to meet you all in person, because what we are missing is basically talking, well, having these discussions offline when the conference wraps up, which is part of usual Plumbers, but I mean, we are losing it with the virtual experience, even though it was very positive anyway, in my opinion, for the second year running. So to complete, I mean, just thank you very much all for attending, for your useful presentations and comments. And I mean, I'll talk to you within LPC tomorrow. I mean, and well, online or offline, I mean, feel free to reach out through the usual channels if anything needs attention. So thank you very much, everybody. And it was a pleasure to run this micro conference. Thank you very much on behalf of everyone organizing it.
Thanks, Lorenzo. Bye-bye.
Yeah, thanks, Lorenzo, and everyone.